The universe is vast, mysterious, and filled with secrets that have puzzled humanity for centuries. It's a boundless expanse of space and time, home to billions of galaxies, stars, planets, and phenomena we are only beginning to understand. Today we embark on a journey to uncover some of the most profound and mind-bending mysteries that define our existence. For as long as we've gazed at the stars, we've asked questions about our origins, our purpose, and the nature of the cosmos. What lies beyond the edges of what we can see? How did everything begin? And where will it all end? These questions push the boundaries of science and ignite the imagination. At the heart of these mysteries is our quest to understand the universe itself. From the smallest subatomic particles to the largest cosmic structures, every discovery brings us closer to answering some of the biggest questions in science. Yet for every answer we uncover, new questions emerge, revealing just how little we know about the reality we inhabit. The universe doesn't easily give up its secrets. Every discovery, from the detection of dark matter to the understanding of black holes, represents years of painstaking work, collaboration, and ingenuity. Scientists and researchers use cutting-edge technology, powerful telescopes, and theoretical models to peel back the layers of the cosmic onion. This journey is not just about science, it's also deeply philosophical. The more we understand the universe, the more we are forced to confront our own place within it. Are we an anomaly in an otherwise empty cosmos? Or are we part of a much larger story, one that connects us to the farthest reaches of space and time? Even the most basic concepts, like time and space, are far more complex than they appear. What we experience in our daily lives is just the surface. Beneath it lies a web of physical laws and forces that govern everything from the movements of galaxies to the behavior of particles. In the face of such vastness, it's easy to feel insignificant. But our ability to ask these questions, to search for answers, and to dream of what's beyond is a testament to the resilience and creativity of the human spirit. Every discovery reminds us that curiosity is one of our most powerful tools. As we dive into the mysteries of the universe, we're not just seeking knowledge for its own sake. We're looking for connections between the stars and ourselves, between the past and the future, between the known and the unknown. The universe isn't just out there, it's within us, shaping our very existence. From the fiery birth of the cosmos to the potential existence of other worlds teeming with life, each revelation expands our understanding of what is possible. The universe invites us to dream bigger, to think beyond the boundaries of what we can see, and to embrace the unknown. The secrets of the universe are a reminder of how far we've come and how much there is still to explore. They challenge us to push the limits of what we know and inspire us to imagine what lies beyond. This is the story of humanity's greatest adventure, the pursuit of cosmic understanding. The Big Bang Theory stands as one of the most profound ideas humanity has ever developed. It proposes that the universe began as an unimaginably hot, dense point, bursting into existence nearly 13.8 billion years ago. This singular moment marked the origin of space, time, and everything we now know. In its earliest fractions of a second, the universe expanded at an astonishing rate in an event known as cosmic inflation. This rapid growth set the stage for the formation of particles, atoms, and eventually stars and galaxies. Everything we see today traces back to this moment of creation. As the universe expanded, it began to cool. In the first few minutes, fundamental particles like protons and neutrons combined to form the nuclei of the simplest elements. Hydrogen and helium became the building blocks for everything that would follow. The faint afterglow of this event, called the cosmic microwave background radiation, is one of the strongest pieces of evidence for the Big Bang. This ancient light, discovered in the 1960s, offers a snapshot of the universe as it appeared just 380,000 years after its birth. Scientists study this radiation to uncover clues about the universe's early structure. Tiny fluctuations in the cosmic microwave background reveal the seeds of galaxies, showing how matter clumped together under the pull of gravity. These patterns are like a fingerprint of the universe's infancy. Another key piece of evidence lies in the abundance of light elements in the cosmos. The precise ratios of hydrogen, helium, and lithium align perfectly with predictions made by Big Bang nucleosynthesis. No other theory explains these proportions as accurately. Despite its success, the Big Bang theory isn't without mysteries. What triggered this event? and what existed, if anything, before it. These are questions that continue to challenge our understanding and push the boundaries of theoretical physics. The theory also raises intriguing possibilities about the ultimate fate of the universe. If it had a beginning, will it also have an end? Could the cosmos collapse back into itself, expand forever, or experience something even more unexpected? Modern research has expanded the story of the Big Bang, incorporating ideas like dark matter and dark energy. These invisible forces seem to have played a critical role in shaping the universe, yet they remain some of science's greatest enigmas. Even as we gather evidence, the concept of the Big Bang is constantly evolving. New discoveries, like those from advanced telescopes and particle accelerators, refine our understanding and reveal new complexities. Science, like the universe itself, is in a state of constant expansion. The Big Bang theory is more than a scientific explanation. It's a testament to human ingenuity and curiosity. It shows how far we've come in understanding our origins and how much more there is to uncover. This foundational idea connects us to the cosmos in a profound way, reminding us that every atom in our bodies was forged in the fiery crucible of the universe's earliest moments. It's a story that continues to unfold, offering endless opportunities for discovery. While the Big Bang theory dominates cosmology, alternative ideas have been proposed to explain the origins of the universe. These theories challenge traditional notions and offer new ways to think about how everything began. Each one brings unique insights while posing its own set of questions. One alternative is the steady-state theory, which suggests that the universe has no beginning or end. In this model, new matter is continuously created as the universe expands, maintaining a constant density over time. Though largely discredited, it sparked valuable debates in cosmology. The cyclic model envisions the universe as part of an endless cycle of expansions and contractions. Instead of a single Big Bang, it proposes a series of bangs and crunches, where each iteration gives rise to a new universe. This concept merges the idea of beginnings with the notion of eternity. Some theories focus on quantum mechanics, suggesting that the universe emerged from a quantum fluctuation. In this view, the laws of physics allow tiny particles to pop into existence, and our universe may have been one such fluctuation on a cosmic scale. This raises intriguing questions about the role of probability in creation. The ekpyrotic theory presents a scenario where the universe was born from the collision of two higher-dimensional branes. These branes, existing in a multidimensional space, generate energy and matter when they interact. It's a model that combines elements of string theory with cosmology. Another perspective comes from the concept of a holographic universe. This theory suggests that the three-dimensional universe we experience may be a projection of information encoded on a two-dimensional surface. If true, it redefines our understanding of space, time, and the very fabric of reality. The multiverse hypothesis introduces the idea that our universe is just one among countless others. In this framework, universes may form constantly through processes like eternal inflation or quantum tunneling. Each one could have its own physical laws and constants, making ours just a small piece of a grander cosmic puzzle. Some scientists explore the idea of a pre-Big Bang universe. Instead of a singular starting point, this view suggests the universe had a previous state, possibly governed by different physical laws. Understanding this prior state could unlock new insights into the origins of everything. The plasma cosmology model offers an entirely different take, emphasizing the role of electromagnetic forces over gravity in shaping the cosmos. It argues that plasma, a state of matter made of charged particles, dominates the universe and drives its evolution. This approach challenges conventional assumptions about cosmic dynamics. Emergent universe theories propose that the cosmos didn't originate from a singular event, but gradually emerged from a timeless state. In these models, the universe transitions from an eternal, unchanging phase into the dynamic, expanding space we observe today. This concept sidesteps the question of what caused the beginning. Some ideas suggest that the universe is a simulation, a creation of advanced intelligence rather than a natural phenomenon. If true, the Big Bang might represent the moment the simulation was initiated, programmed to mimic the laws of physics we observe. This theory blurs the line between science and philosophy. While none of these alternatives has yet displaced the Big Bang theory, they highlight the creativity and depth of human thought. Each one challenges us to think beyond established paradigms and consider new possibilities for the origin and nature of the universe. These ideas, even when speculative, expand our horizons and deepen the mystery of existence. Cosmic inflation plays a pivotal role in our understanding of the early universe. It suggests that, in the first fractions of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This rapid growth set the foundation for everything we observe in the cosmos today. During inflation, tiny quantum fluctuations were stretched to cosmic scales. These fluctuations became the seeds for the formation of galaxies, clusters, and the large-scale structure of the universe. Without this process, the universe would look vastly different, lacking the intricate patterns we see now. Inflation also provides an explanation for the incredible uniformity of the cosmic microwave background radiation. Despite vast distances, regions of the universe appear strikingly similar in temperature and composition. This homogeneity would be difficult to explain without the smoothing effect of inflation. One of the key predictions of inflation is the existence of primordial gravitational waves. These ripples in spacetime, generated during the inflationary phase, carry information about the universe's earliest moments. Detecting these waves would provide direct evidence for inflation and validate the theory. Another mystery inflation resolves is the flatness problem. Observations show that the universe's geometry is remarkably flat, meaning space isn't curved in any significant way. Inflation explains this by stretching the fabric of the universe, making any initial curvature negligible. Inflation also addresses the horizon problem, which asks how regions of the universe that have never interacted could appear so similar. By rapidly expanding the early universe, inflation allowed these regions to share information before they were stretched beyond each other's reach. Different models of inflation propose varying mechanisms for how this phase occurred. Some suggest the existence of an inflationary field, driven by a hypothetical particle called the inflaton. The behavior of this field dictates the timing and scale of inflation. While inflation is widely accepted, it raises its own questions. What triggered this exponential expansion, and why did it end? Understanding these mechanisms is a central challenge in modern cosmology, requiring insights from both physics and mathematics. Some scientists explore whether inflation could lead to the creation of multiple universes. If inflation occurred in patches, with some regions continuing to expand, it could result in a multiverse, where our universe is just one of countless others. Inflation connects the quantum world to the cosmic scale, linking tiny particles with the vast expanse of space. This bridge between the small and the large is one of the most profound aspects of the theory, showing how fundamental physics shapes the universe at every level. The evidence for inflation continues to grow, supported by observations of the cosmic microwave background and the distribution of galaxies. These findings align with predictions made decades ago, reinforcing the idea that inflation was a critical phase in the universe's evolution. As we delve deeper into the nature of inflation, we uncover more about the origins of the cosmos. It's a story of rapid expansion, incredible transformations, and the intricate processes that gave rise to the universe we see today. Inflation remains a cornerstone of modern cosmology, shaping our quest to understand the fundamental workings of reality. The earliest moments of the universe were dominated by extreme temperatures and densities, conditions far beyond anything we can experience today. This was a time when energy and matter were indistinguishable, a chaotic state governed by the laws of quantum mechanics. Everything that would become the universe was compressed into an incredibly small space. As the universe began to expand, it cooled rapidly, allowing particles to start forming. Quarks and gluons, the fundamental building blocks of matter, emerged from the initial energy soup. These particles combined to form protons and neutrons, the first components of atomic nuclei. During the first fractions of a second, the fundamental forces of nature began to separate. Gravity, the weakest but most far-reaching force, split off first, followed by the strong nuclear force, the weak nuclear force, and electromagnetism. This process laid the groundwork for the interactions that shape the universe. The timeline of these moments is incredibly precise. Within the first microsecond, the universe transitioned from a state of pure energy to one where matter began to dominate. This shift marked the start of the journey toward the complex structures we see today. A few seconds after the Big Bang, conditions cooled enough for nucleosynthesis to begin. Protons and neutrons collided, forming the nuclei of the lightest elements, primarily hydrogen and helium. These elements would later serve as the raw materials for stars and galaxies. Despite its rapid expansion, the universe remained opaque for hundreds of thousands of years. High-energy photons were constantly interacting with charged particles, preventing light from traveling freely. This dense, glowing plasma filled the cosmos, masking the universe's structure. Eventually, as the universe cooled further, electrons combined with nuclei to form neutral atoms. This event, known as recombination, allowed light to decouple from matter, creating the cosmic microwave background. This faint glow is a snapshot of the universe at just 380,000 years old. Recombination marked the end of the universe's earliest phase and the beginning of a new era. With light free to travel, the universe became transparent, allowing energy to flow and matter to gather under the influence of gravity. This set the stage for the formation of stars and galaxies. The first structures in the universe formed from tiny density fluctuations in the primordial plasma. These ripples, amplified by gravity, created the seeds for galaxies, clusters, and the vast cosmic web we observe today. They represent the earliest imprints of cosmic order. The transition from chaos to structure was a delicate balancing act. The interplay of expansion, gravity, and cooling determined how the universe evolved. Any slight change in these conditions could have led to a completely different cosmos, or no universe at all. Modern telescopes and experiments aim to peer even further back, closer to the moment of the Big Bang. By studying phenomena like gravitational waves and high-energy particles, scientists hope to uncover more about the universe's earliest moments. These observations could reveal the fundamental processes that shaped everything. Understanding the first moments of the universe is key to understanding ourselves. Every particle, every atom, and every star traces its origins to this incredible era. It's a reminder that the story of the cosmos is also the story of where we come from. Even with decades of research, the beginning of the universe remains shrouded in mystery. We still don't know what triggered the Big Bang, or if there was something before it. These questions challenge the limits of both science and philosophy. One of the most intriguing mysteries is the cause of cosmic inflation. While the theory explains much about the early universe, the mechanism driving this rapid expansion is still unknown. What force or process could have created such an extraordinary event? The singularity itself poses a significant puzzle. If everything in the universe was once compressed into an infinitely small point, what does that say about the nature of space, time, and matter? Understanding this singularity could rewrite the rules of physics. The concept of time before the Big Bang is another enigma. Did time itself begin with the universe, or is it part of a larger framework we cannot yet comprehend? These ideas push the boundaries of human understanding, venturing into the realm of the unknown. The role of quantum mechanics in the universe's birth raises further questions. Theories suggest the early universe was governed by quantum laws, but bridging the gap between quantum mechanics and general relativity remains one of science's greatest challenges. A unified theory could unlock answers about the very beginning. Dark matter and dark energy also add layers of mystery to the origin story. If these invisible forces shaped the universe from its earliest moments, what are they, and how did they come to exist? Their role in the beginning remains speculative but essential. The potential existence of other dimensions complicates the picture. Some theories propose that higher dimensions influenced the birth of the universe or even gave rise to it. These dimensions, if real, could hold the key to understanding the mechanisms of creation. The idea of multiple universes raises the possibility that ours is not unique. Was the Big Bang just one of countless events creating universes in an endless cycle? If so, exploring this cosmic landscape could redefine our place in the multiverse. Some physicists question whether the Big Bang was truly the beginning. Could it have been a transition from one state of the universe to another? This concept suggests that the universe might have existed in some form indefinitely, with the Big Bang as just one phase. The relationship between entropy and the beginning of the universe is another unresolved issue. Why did the early universe start in such a highly ordered low-entropy state? Understanding this could shed light on why the universe evolves the way it does. Experimental evidence for these mysteries remains elusive. Tools like particle accelerators and space telescopes provide glimpses into the past, but the conditions of the early universe are difficult to replicate or observe directly. New technology and innovative ideas are essential to move forward. The beginning of the universe is a story still waiting to be told in full. Every discovery brings us closer, but each answer seems to unveil deeper questions. The mystery of our origins continues to inspire and challenge us, driving the quest to understand the ultimate truth. Dark matter is one of the most perplexing substances in the universe. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet its presence is undeniable, revealed through its gravitational effects on galaxies and cosmic structures. Galaxies spin at speeds that should tear them apart if only visible matter were present. Dark matter provides the extra mass needed to hold them together. This unseen substance acts as a cosmic glue, ensuring the stability of galaxies across billions of years. The influence of dark matter extends to the largest structures in the universe. Galaxy clusters, interconnected by filaments of dark matter, form the cosmic web. This vast framework shapes the distribution of galaxies and the evolution of the cosmos. One of the earliest clues to dark matter came from observations of the Coma cluster in the 1930s. Astronomer Fritz Zwicky noticed galaxies within the cluster were moving too fast for the visible mass to account for their motion. This was one of the first pieces of evidence for unseen matter. Today we estimate that dark matter makes up about 27% of the universe's total energy density. In comparison, all the stars, planets, and observable matter account for just 5%. The sheer scale of dark matter's presence suggests it plays a fundamental role in the cosmos. Despite its prevalence, we don't know what dark matter is made of. It could consist of exotic particles, unlike anything found in the standard model of physics. These particles, if they exist, would interact only through gravity and possibly the weak nuclear force. One leading candidate for dark matter is the WIMP, or weakly interacting massive particle. Scientists have been searching for these elusive particles using underground detectors and particle accelerators. So far, the results have been inconclusive, leaving the mystery unsolved. Another possibility is axions, ultralight particles that could account for dark matter. These particles are theorized to have unique properties, such as forming waves instead of behaving like traditional particles. Efforts to detect axions are ongoing, using innovative methods like tuning microwave cavities. Some theories propose that dark matter could be made of primordial black holes. These small, ancient black holes might have formed shortly after the Big Bang and now contribute to the invisible mass we observe. However, this idea remains speculative and difficult to test. Alternative explanations challenge the very existence of dark matter. Modified theories of gravity, like MOND, suggest changes to our understanding of gravity could explain the observed phenomena. While intriguing, these theories face significant challenges and have yet to gain widespread acceptance. The search for dark matter is pushing the limits of technology and science. From massive underground detectors to experiments in space, every effort brings us closer to unraveling its nature. Each null result refines our understanding and narrows the possibilities. Dark matter holds the key to understanding the universe's structure and history. Though invisible, its presence is felt everywhere, shaping the cosmos in ways we are only beginning to grasp. The quest to uncover its secrets is one of the most exciting frontiers in modern science. Galactic rotation curves provide some of the most compelling evidence for the existence of dark matter. When astronomers measure the speed of stars orbiting within galaxies, they find something surprising. Instead of slowing down at the edges as predicted by visible mass, the stars maintain unexpectedly high speeds. This phenomenon was first studied in detail in the 1970s by Vera Rubin and her colleagues. They observed that in spiral galaxies, the outer stars were moving too fast for the gravitational pull of the visible matter alone. This implied the presence of an unseen mass exerting additional gravitational force. The rotation curves of galaxies are plotted as graphs, showing the relationship between distance from the galactic center and orbital velocity. For most galaxies, these curves remain flat far beyond where visible matter exists. This flatness is a signature that points directly to dark matter. If only visible matter were present, the curve would show a steep decline at the galaxy's outer regions. The gravitational influence of stars, gas, and dust diminishes with distance, yet the observed speeds defy this expectation. Dark matter provides the necessary mass to explain these observations. What's remarkable is that this behavior is not unique to a few galaxies. Flat rotation curves have been observed in countless spiral galaxies across the universe. This consistency strengthens the case for dark matter as a universal component of galactic dynamics. The amount of dark matter needed to account for these speeds is staggering. In many galaxies, the dark matter outweighs the visible matter by a factor of 5 to 1. This dominance suggests that galaxies are embedded in vast halos of invisible material. These dark matter halos are thought to extend far beyond the visible boundaries of galaxies. They provide the gravitational framework that holds galaxies together, preventing them from flying apart, despite their high rotational speeds. Without dark matter, the structure of galaxies would be entirely different. Observations of dwarf galaxies also reveal the same pattern. These small, faint galaxies show rotation curves that similarly indicate the presence of dark matter. The fact that dark matter's influence spans such a wide range of galactic types adds to its credibility. Even in galaxies with less active star formation, where visible matter is less concentrated, rotation curves still suggest significant dark matter. This implies that dark matter's presence is not dependent on the characteristics of the stars or gas, but is a fundamental part of galactic structure. Advanced simulations of galaxy formation incorporate dark matter to recreate rotation curves. These models consistently match observed data, further validating the role of dark matter in shaping galaxies. Without it, the simulations fail to produce realistic results. Galactic rotation curves also challenge alternative theories that attempt to explain these dynamics without dark matter. While some modified gravity models can mimic the effects, they often struggle to account for the full range of observations across different galaxies. The evidence from rotation curves has transformed our understanding of the universe. By revealing the hidden mass that dominates galactic behavior, these observations highlight just how much remains to be discovered about the cosmos. The mystery of what makes up this dark matter continues to drive some of the most ambitious scientific efforts today. The composition of dark matter remains one of the greatest mysteries in astrophysics, but several leading theories attempt to explain its nature. At the forefront are WIMPs, or weakly interacting massive particles, hypothetical particles that interact through gravity and the weak nuclear force. These particles could explain the abundance and behavior of dark matter across the universe. Axions are another intriguing candidate, theorized as incredibly light particles that interact minimally with normal matter. Unlike WIMPs, axions could behave like waves, and their properties might align with certain astrophysical observations. Experiments are underway to detect their subtle effects, particularly through their potential interaction with electromagnetic fields. Sterile neutrinos offer yet another possibility. These particles would be a heavier, non-interacting version of the familiar neutrinos that play a role in nuclear reactions. Their elusive nature makes them difficult to detect, but they could account for the mysterious mass attributed to dark matter. Primordial black holes are a more exotic theory. These small black holes formed shortly after the Big Bang could make up the dark matter we observe today. Although their existence has not been confirmed, they remain a fascinating possibility that bridges astrophysics and cosmology. Some theories suggest that dark matter could consist of particles from an entirely new sector of physics. This hidden sector would operate with its own rules and forces, interacting with our universe only through gravity. Such an idea opens up the potential for a completely unknown branch of science. Another perspective is the idea of fuzzy dark matter, composed of ultralight particles with wavelengths comparable to galaxies. This theory could explain certain galactic behaviors that other models struggle with, particularly in low-mass systems like dwarf galaxies. Self-interacting dark matter proposes that dark matter particles interact with each other, unlike the cold and collisionless particles of traditional models. These interactions might create effects that influence galactic shapes and distributions, providing a more dynamic picture of dark matter. A fascinating theoretical possibility is that dark matter might be composed of exotic compact objects, such as quark nuggets or strangelets. These would be dense clumps of matter formed under extreme conditions in the early universe. While speculative, such objects could help explain some observational anomalies. Supersymmetry, a theoretical extension of the standard model of particle physics, offers a range of potential dark matter candidates. Particles like the neutralino could emerge as stable, massive particles under supersymmetric frameworks, fitting the profile of dark matter. Dark matter may even be more than one thing. Some models propose a combination of components, including both particles and macroscopic objects, that together create the effects we observe. This hybrid approach could reconcile conflicting evidence from different observations. The idea of mirror matter suggests that dark matter could be a parallel version of the ordinary particles we know. This hidden mirror universe would interact weakly with ours, contributing gravitational effects without being directly observable. It's a speculative but intriguing concept. While none of these theories have been conclusively proven, each brings us closer to understanding what dark matter might be. The search for its composition is pushing the boundaries of physics, driving innovation in experiments, and expanding the frontiers of human knowledge. Detecting dark matter is one of the most ambitious goals in modern physics, requiring sophisticated experiments to uncover its elusive nature. Scientists have developed a variety of methods to search for signs of dark matter, each designed to capture its faint signals in different ways. These efforts span underground labs, particle accelerators, and even outer space. Direct detection experiments focus on identifying dark matter particles interacting with normal matter. Sensitive detectors, often placed deep underground to shield them from background noise, aim to observe rare collisions between dark matter particles and atomic nuclei. So far, these experiments have set tighter constraints on how dark matter might behave. One prominent example is the xenon-based experiments, which use liquid xenon as a target material. If a dark matter particle collides with a xenon nucleus, it would produce a faint flash of light or release electrons, signaling its presence. Despite extensive searches, no definitive signals have been found yet. Another approach involves searching for dark matter indirectly by studying its potential byproducts. Dark matter particles might annihilate or decay, releasing high-energy particles like gamma rays or neutrinos. Observatories such as the Fermi Gamma Ray Space Telescope are scanning the universe for these signals. Particle accelerators like the Large Hadron Collider explore the possibility of creating dark matter in high-energy collisions. By smashing protons together at nearly the speed of light, physicists hope to produce particles that match dark matter's predicted properties. Although no direct evidence has emerged, the experiments provide critical data for refining theories. Cosmic ray detectors also play a role in the search. Instruments like AMS-02, mounted on the International Space Station, look for unusual patterns in cosmic rays that could hint at dark matter interactions. These anomalies, if confirmed, might offer indirect clues about its existence. Axion detection experiments take a different approach, focusing on electromagnetic interactions. Devices like resonant cavities or magnetized environments are designed to detect the subtle conversion of axions into photons. These experiments require extreme precision, pushing the limits of modern technology. Gravitational lensing studies offer another window into dark matter. By observing how dark matter bends light from distant galaxies, astronomers can map its distribution and infer its properties. While this method doesn't detect particles directly, it provides invaluable insight into dark matter's role in the cosmos. Space-based detectors like the upcoming Euclid mission and the James Webb Space Telescope aim to further study dark matter's effects on large-scale cosmic structures. These instruments could reveal patterns and distributions that ground-based observatories cannot see, deepening our understanding of dark matter's influence. Researchers are also exploring innovative ideas like quantum sensors, which could detect extremely subtle shifts caused by dark matter. These cutting-edge devices promise new possibilities for capturing evidence where traditional methods have fallen short. Experimental collaborations across the globe are key to this search. Projects like Lux, Zeppelin, IceCube, and Dharma Libra combine expertise from multiple disciplines, creating a worldwide effort to uncover the nature of dark matter. This collaborative spirit drives progress and inspires new approaches. Each experiment, whether it finds dark matter or not, contributes to refining our understanding of the universe. The absence of detection so far only deepens the mystery, pushing scientists to design even more sensitive and creative experiments in the quest to solve this cosmic puzzle. Dark matter is an essential component of the universe, shaping its structure and evolution in profound ways. Without it, galaxies, clusters, and the cosmic web as we know them could not exist. Its gravitational pull influences how matter clumps together, creating the scaffolding for all visible structures. During the early universe, dark matter played a crucial role in forming the first galaxies. While normal matter was influenced by radiation and pressure, dark matter, unaffected by these forces, began to collapse under gravity. These dense regions acted as seeds, drawing in gas that would eventually ignite as stars. Dark matter halos surround galaxies, extending far beyond the visible edges. These halos stabilize galaxies, preventing them from being torn apart by their own rotational speeds. Without this unseen mass, the dynamic behavior of stars and gas within galaxies would not make sense. On larger scales, dark matter forms the backbone of the cosmic web, the vast network of filaments connecting galaxies and clusters. These filaments are made of dark matter, with visible galaxies forming along their dense intersections. This web-like structure is the framework of the universe. The gravitational influence of dark matter helps galaxies cluster together into massive groups. These clusters, some containing thousands of galaxies, are held together by dark matter's immense gravitational pull. It also binds intracluster gas, which emits X-rays that we can observe. Even individual galaxies owe their shape and stability to dark matter. Spiral galaxies, with their thin, flat disks, rely on dark matter halos to maintain their structure over billions of years. Elliptical galaxies, too, are surrounded by dark matter that dictates their formation and dynamics. Dark matter also affects how galaxies interact. When galaxies collide or merge, their dark matter halos influence the outcome, often leading to new structures like tidal tails or starburst regions. These interactions are guided not only by visible matter, but by the vast reservoirs of dark matter surrounding each galaxy. Gravitational lensing caused by dark matter shapes how we view distant objects. When light from faraway galaxies passes near a massive concentration of dark matter, it bends and magnifies, creating distorted or multiple images. This phenomenon allows astronomers to map dark matter distributions indirectly. The effects of dark matter extend to the formation of stars and planetary systems. By anchoring gas and dust within galaxies, dark matter creates the environments where star formation can occur. Over time, this process leads to the creation of planets and potentially life. The evolution of the universe itself is deeply tied to dark matter. Its gravitational influence slowed the initial expansion after the Big Bang, allowing structures to form. Without it, the universe would be a vastly different, more diffuse place, devoid of the complexity we see today. Simulations of cosmic evolution rely heavily on dark matter to recreate the observed universe. When included in models, dark matter accurately predicts the large-scale distribution of galaxies and the growth of structures over time. These simulations confirm its critical role in shaping the cosmos. Though invisible, dark matter is the silent architect of the universe, influencing every level of its structure. From the smallest dwarf galaxies to the largest superclusters, it binds the cosmos together, leaving an imprint on everything we observe. Understanding its role is essential to unraveling the story of the universe. The discovery of the universe's acceleration was a groundbreaking moment in cosmology, reshaping our understanding of its fate. In the late 1990s, two independent teams of astronomers studied distant supernovae to measure the expansion rate of the universe. What they found defied expectations. The universe wasn't slowing down, it was speeding up. These supernovae, known as type Ia, are incredibly bright and consistent, making them reliable cosmic yardsticks. By observing how their light stretched as it traveled through expanding space, astronomers could calculate the rate of expansion over time. The data revealed a puzzling truth. The expansion rate was increasing. This acceleration implied the existence of a mysterious force counteracting gravity, now known as dark energy. Unlike dark matter, which pulls things together, dark energy pushes them apart. It dominates the universe, accounting for nearly 70% of its total energy density. The discovery was so unexpected that it earned the 2011 Nobel Prize in Physics. For decades, scientists had assumed gravity would slow the expansion, possibly leading to a collapse or a stable equilibrium. The idea that the universe was accelerating came as a profound surprise. One of the most striking aspects of dark energy is its apparent constancy. Unlike matter, which clusters and evolves, dark energy seems evenly distributed throughout space, exerting its influence uniformly. This strange behavior challenges our understanding of physics. Observations of the cosmic microwave background provide further evidence for acceleration. The patterns in this ancient light, combined with data from galaxy surveys, confirm that dark energy began dominating the universe billions of years ago. Its effects have only grown stronger with time. Dark energy's influence is felt on the largest scales. It affects the rate at which galaxies move away from each other and determines the ultimate fate of the cosmos. Without it, the universe's history and future would look drastically different. The discovery of acceleration also raised new questions about the nature of space itself. Some theories suggest that dark energy is tied to the vacuum of space, an inherent property that exerts pressure as the universe expands. Others propose it may be linked to fields or particles we have yet to understand. Experiments like those using baryon acoustic oscillations provide additional support. These patterns in the distribution of galaxies offer a way to trace the history of cosmic expansion, consistently pointing to the presence of dark energy. The evidence grows stronger with every new observation. Despite its central role in cosmology, dark energy remains one of the biggest enigmas in science. It challenges the standard model of physics, hinting at a deeper, more fundamental layer of reality. Understanding it could unlock entirely new principles of the universe. The discovery also changed how we think about the universe's timeline. If the acceleration continues unchecked, galaxies will drift further apart, stars will burn out, and the cosmos could end in a cold, dark expanse. This scenario, known as the Big Freeze, is a stark contrast to previous expectations. The accelerated expansion of the universe is a reminder of how much we have yet to learn. It underscores the vastness of the cosmos and the mysteries it holds, driving scientists to explore further in their quest to understand the forces shaping existence. Dark energy and the expansion of the universe are intricately connected, with dark energy driving the accelerating growth of space. As the universe expands, dark energy exerts a repulsive force, counteracting the pull of gravity. This dynamic shapes the cosmos on the largest scales, influencing its past, present, and future. Unlike matter, which dilutes as the universe grows, dark energy remains constant in density. This property ensures its influence becomes more dominant over time, pushing galaxies further apart. It's a force that behaves unlike anything else in physics. The expansion itself affects how dark energy operates. As space stretches, the additional volume is filled with the constant density of dark energy, meaning its total influence grows with the size of the universe. This feedback loop is what accelerates the cosmic expansion. The relationship between dark energy and the expansion is evident in the universe's history. Early on, gravity, driven by matter, slowed the rate of expansion. But as the universe grew and matter spread out, dark energy began to dominate, reversing this trend and accelerating the expansion. Dark energy's effects are most noticeable on intergalactic scales. Within galaxies, gravity remains strong enough to hold stars and planets together. But beyond these boundaries, dark energy's push overwhelms gravitational attraction, causing galaxies to drift apart faster over time. One of the puzzles in this relationship is the timing of dark energy's dominance. It's unclear why this force began accelerating the universe billions of years after the Big Bang. Understanding this timing could provide insights into the nature of dark energy and its origins. Some scientists theorize that dark energy is tied to the vacuum energy of space itself. If this is true, the expansion of the universe simply reveals the properties of empty space. But this explanation leaves unanswered questions about why its effects are so precisely balanced with the expansion. Another perspective suggests that dark energy might evolve over time. In this model, the force driving expansion could change in strength or nature, leading to different scenarios for the universe's ultimate fate. Observations are still testing these ideas. The interplay between dark energy and expansion also impacts the structure of the universe. It affects how galaxies form and cluster, preventing them from growing as large as they might in a universe without dark energy. Its influence is written into the very architecture of the cosmos. Current measurements show that the expansion rate, driven by dark energy, is accelerating. This phenomenon, described by the Hubble constant, is central to modern cosmology. However, discrepancies in its precise value across different methods of measurement highlight how much remains uncertain. Simulations of the universe incorporate dark energy to recreate observed phenomena. These models show that without it, the universe would not expand in the same way. Its inclusion is critical for matching theory with reality, yet its exact properties remain elusive. The relationship between dark energy and expansion is one of the most profound aspects of the universe. It reveals how a single force can shape the destiny of everything, from galaxies to the vast emptiness of space. Exploring this connection continues to challenge and expand our understanding of the cosmos. Quintessence and lambda CDM represent two leading theories in the effort to explain dark energy and the accelerating universe. Each offers a distinct view of the mysterious force driving cosmic expansion, yet both grapple with profound questions about its nature and origins. These competing models illustrate the diversity of thought in modern cosmology. Lambda CDM, often referred to as the standard model of cosmology, is built around the concept of a cosmological constant. This constant, represented by the Greek letter lambda, assumes that dark energy is an unchanging property of space itself. It provides a simple, elegant explanation for the observed acceleration of the universe. In lambda CDM, dark energy's density remains constant over time, regardless of how the universe expands. This model aligns well with most observational data, making it a widely accepted framework. However, it leaves open questions about why dark energy has the specific value it does and what its true nature might be. Quintessence, on the other hand, proposes a dynamic form of dark energy. Unlike the cosmological constant, quintessence allows the properties of dark energy to change over time. This variation could explain why dark energy only began dominating the universe billions of years after the Big Bang. In the quintessence model, dark energy is often described as a field, similar to those in particle physics, that evolves as the universe expands. Its strength and influence might increase or decrease, depending on the conditions of the cosmos. This flexibility gives quintessence the potential to address certain gaps left by the lambda CDM model. One of the key differences between these theories lies in their predictions for the universe's future. Lambda CDM suggests a steady, unchanging acceleration, while quintessence allows for scenarios where the acceleration might slow, halt, or even reverse. Observations over the coming decades may help distinguish between these possibilities. The simplicity of lambda CDM is both its strength and its limitation. By assuming a constant dark energy density, the model fits current data with minimal assumptions. Yet it doesn't explain why dark energy has the precise value needed to accelerate the universe at this time. Quintessence, though more complex, offers a broader framework for understanding dark energy. It could account for variations in the universe's expansion history, or provide insights into how dark energy interacts with other cosmic forces. However, this complexity also makes it harder to test and refine. Both models must contend with observational challenges, particularly in measuring the Hubble constant. Discrepancies between local and cosmic measurements of the universe's expansion rate raise questions about the assumptions underlying both lambda CDM and quintessence. Resolving these tensions could reshape our understanding of dark energy. The cosmic microwave background and large-scale galaxy surveys are critical in evaluating these theories. Lambda CDM currently fits most of the data from these observations, but future experiments could reveal subtle variations that favor quintessence. These tools are essential for testing and refining both models. Despite their differences, lambda CDM and quintessence share a common goal: to explain the mysterious force shaping the universe. Each offers valuable insights, and the competition between them drives innovation in both theory and observation. Exploring these ideas brings us closer to unraveling the true nature of dark energy. The interplay between these theories highlights the complexity of the cosmos. Whether dark energy is a constant property of space or a dynamic, evolving field, understanding it requires both creativity and precision. These models are stepping stones in the journey to decode the universe's most profound mysteries. Dark energy holds the key to the universe's ultimate destiny, shaping its long-term evolution in profound and mysterious ways. Its repulsive force counteracts gravity, driving galaxies apart and determining whether the cosmos expands forever or reaches an unexpected conclusion. The fate of everything depends on its nature and behavior over time. In a universe dominated by dark energy, expansion continues to accelerate. Over billions of years, galaxies will drift so far apart that they become isolated, their light unable to reach one another. This scenario, known as the Big Freeze, envisions a cosmos that grows colder and darker as stars burn out. Dark energy could also lead to an even more dramatic outcome known as the Big Rip. If its strength increases over time, it could overcome not only gravity, but also the forces that hold matter together. In this case, galaxies, stars, and even atoms would be torn apart, ending the universe in a cascade of disintegration. Alternatively, if dark energy behaves differently than we currently predict, it might reverse its effects. A weakening of dark energy could allow gravity to reclaim dominance, causing the universe to slow its expansion. In this scenario, a big crunch could occur, with everything collapsing back into a singularity. The interplay between dark energy and matter also influences how structures evolve. In an accelerating universe, the formation of new galaxies slows, and existing ones are prevented from merging into larger systems. This stunts the growth of cosmic structures, leaving the universe increasingly empty and fragmented. Dark energy's impact isn't limited to the distant future. It has already shaped the cosmos we observe today. By driving acceleration over billions of years, it has influenced the distribution of galaxies and the patterns in the cosmic microwave background. These imprints reveal how deeply tied dark energy is to the universe's history. The nature of dark energy also affects the balance between cosmic forces. While gravity works to pull matter together, dark energy pushes space apart, creating a delicate tug-of-war. Understanding how this balance evolves is essential to predicting the universe's trajectory. Simulations of cosmic evolution highlight how dark energy changes the pace of expansion. Early in the universe, when matter dominated, structures formed more rapidly. But as dark energy became the dominant force, the rate of expansion increased, halting the formation of new large-scale systems. Whether the universe expands forever, tears apart, or collapses depends on the precise properties of dark energy. If it truly behaves as a cosmological constant, the Big Freeze is the most likely outcome. But if it varies, the possibilities remain open to dramatic changes we can only theorize about. Some theories suggest dark energy could evolve into new forms, leading to unexpected transformations in the universe. These shifts might create conditions for another Big Bang, a renewal of cosmic cycles, or entirely novel phenomena beyond our comprehension. Observations of distant supernovae, galaxy clusters, and the cosmic microwave background provide crucial data for understanding dark energy's role. As telescopes and experiments improve, they refine our models, bringing us closer to predicting the universe's fate with greater certainty. The cosmic future is written in the fabric of dark energy, an enigmatic force that shapes every level of existence. Its influence extends from the vast reaches of space to the ultimate destiny of the universe itself, ensuring its mysteries remain at the heart of cosmological exploration. Measuring and understanding dark energy presents some of the most daunting challenges in modern science. Unlike matter, which can be observed directly, dark energy is inferred through its effects on the universe's expansion. This indirect nature makes studying it a complex and delicate process. One of the primary difficulties is its uniform distribution across space. Dark energy doesn't clump or gather like matter, so it leaves no direct observational trace. Scientists rely on the subtle imprint it leaves on cosmic phenomena, such as supernovae, or the large-scale structure of the universe. Supernova measurements have provided critical evidence for dark energy, but even these are not without challenges. Observing these distant, faint explosions requires extremely precise instruments, and interpreting the data depends on understanding their behavior across billions of years. Any uncertainty can complicate the results. The cosmic microwave background is another key source of information, but its signals must be carefully disentangled from other effects. Variations in this ancient light provide clues about dark energy's influence on the universe, yet separating those signals from noise requires incredible precision and sophisticated models. Galaxy surveys offer another way to probe dark energy, mapping the distribution of galaxies over time and space. However, these surveys must account for factors like gravitational lensing, redshift, and the motion of galaxies, each of which can obscure the underlying effects of dark energy. The Hubble constant, a measure of the universe's expansion rate, presents its own set of challenges. Different methods of calculating it, such as using nearby galaxies versus distant cosmic features, yield slightly different values. Resolving this tension is crucial for understanding dark energy's role in the expansion. Dark energy's effects are subtle, and often compete with other forces, such as gravity or the dynamics of dark matter. These overlapping influences make it difficult to isolate the exact contributions of dark energy. Advanced simulations and models are needed to account for these complexities. Theoretical challenges are equally significant. Existing physics struggles to explain why dark energy has the specific properties it does, such as its constant density. Reconciling these observations with the standard model of particle physics requires either new particles, forces, or entirely novel theories. Quantum mechanics and general relativity, two pillars of modern physics, don't currently provide a unified explanation for dark energy. Bridging this gap is essential to understanding the fundamental nature of the force, yet no consensus has emerged on how to do so. Experimental limitations also play a role. Many of the tools used to study dark energy, such as space telescopes or particle accelerators, are constrained by their sensitivity, resolution, and scope. Developing more advanced technologies is critical to pushing the boundaries of what we can detect and measure. Another challenge lies in testing alternative explanations. Some theories propose modifications to gravity or other cosmic forces rather than invoking dark energy itself. Disentangling these possibilities from the standard model requires a wide range of experiments and observations to compare predictions. Despite these obstacles, every step forward deepens our understanding. Each new measurement, even when it raises more questions, contributes to the broader picture of this enigmatic force. The journey to unravel dark energy's mysteries continues to push the limits of human knowledge and creativity. Black holes form when matter is compressed into an incredibly small space, creating a gravitational pull so strong that nothing, not even light, can escape. This process typically occurs in the aftermath of a massive star's life cycle. When the star exhausts its nuclear fuel, it collapses under its own gravity. For stars much larger than our Sun, the collapse can be catastrophic, leading to a supernova explosion. The outer layers are ejected into space, while the core compresses into an infinitely dense point called a singularity. This singularity becomes the heart of the black hole. The formation of a black hole depends on the star's mass. Only stars with a mass roughly 3 times greater than the Sun are capable of collapsing into black holes. Smaller stars, like the Sun, end their lives as white dwarfs or neutron stars instead. A black hole's boundary, known as the event horizon, marks the point of no return. Once anything crosses this threshold, it is irreversibly pulled toward the singularity. The size of the event horizon is proportional to the black hole's mass, defining the region of its influence. In some cases, black holes form through the merging of neutron stars. These collisions release enormous amounts of energy and create a black hole at their center. Such events are now detectable through gravitational wave observatories, providing new insights into the process. Supermassive black holes, millions or even billions of times the mass of the Sun, form differently. They are believed to grow over time by consuming matter and merging with other black holes. These giants sit at the centers of most galaxies, including our own Milky Way. Primordial black holes are another possibility, thought to have formed in the early universe. Unlike those created by collapsing stars, these could have emerged from density fluctuations shortly after the Big Bang. If they exist, they might help explain certain mysteries about dark matter. The environment surrounding a black hole also plays a role in its formation. Accretion disks of gas and debris often form as material spirals toward the event horizon. The intense friction and heat in these disks emit powerful radiation, revealing the presence of the otherwise invisible black hole. As black holes consume matter, they grow in size and mass. This process, called accretion, can lead to dramatic changes in their behavior. The largest black holes can devour entire stars, releasing bursts of energy that influence their surroundings. Sometimes black holes form in pairs or as part of larger systems. When they orbit each other, they emit gravitational waves, ripples in space-time that carry energy away. Eventually, these black holes merge, creating a single larger black hole. Not all black holes are born from stars. In theory, sufficiently dense regions of space could collapse directly into black holes under the right conditions. This process might occur in exotic scenarios or in environments with extreme gravitational forces. The formation of black holes is a fundamental process that shapes galaxies and drives cosmic evolution. By studying how they come into being, we gain a deeper understanding of the universe's most powerful and mysterious phenomena. Each discovery reveals more about the forces that govern existence on the grandest scales. The event horizon is the defining boundary of a black hole, a point where gravity becomes so intense that escape is impossible. It marks the threshold beyond which nothing, not even light, can return. For an outside observer, it represents the edge of the unknowable. At the core of the black hole lies the singularity, a region where matter is crushed into infinite density. This singularity is the source of the black hole's immense gravitational pull. It defies the known laws of physics, presenting a challenge to our understanding of the universe. The event horizon and the singularity are deeply connected, but they are not the same. While the singularity exists at the very center, the event horizon is the outermost boundary. Together they define the unique structure of a black hole. As an object approaches the event horizon, time and space become distorted due to the intense gravity. For an outside observer, the object appears to slow down, never quite crossing the horizon. This phenomenon, called gravitational time dilation, is a prediction of Einstein's theory of general relativity. Inside the event horizon, all paths lead inexorably toward the singularity. Space and time switch roles, meaning that moving forward in time is the same as moving closer to the core. Escape is not just unlikely, it's physically impossible. The size of the event horizon depends on the mass of the black hole. For stellar mass black holes, the horizon may be just a few kilometers across, while for supermassive black holes, it can span millions of kilometers. This size defines the region of influence for the black hole's gravity. The singularity itself is hidden behind the event horizon, making it impossible to observe directly. Its existence is inferred through mathematics and the effects it has on surrounding space. It represents a breakdown of our current understanding of physics. The conditions near the singularity are extreme, with gravity compressing matter and energy to unimaginable levels. At these scales, quantum effects likely become significant, but no current theory successfully combines quantum mechanics with general relativity to describe what truly happens. Theories suggest that the singularity might not be a single point, but rather a region governed by unknown physical laws. Concepts like loop quantum gravity or string theory aim to resolve the paradoxes surrounding it, offering glimpses of a deeper reality. The event horizon is more than a boundary. It's a dynamic region influenced by the black hole's spin and interactions. Rotating black holes, known as Kerr black holes, have distorted horizons that create additional phenomena, such as frame dragging. The singularity may also play a role in cosmic events like the formation of jets or the production of gravitational waves. These high-energy phenomena offer indirect evidence of the singularity's power, even if we cannot observe it directly. Studying the event horizon and singularity reveals the extremes of space and time. They are windows into the most mysterious aspects of the universe, where the familiar rules of physics break down, inviting us to explore the unknown. Supermassive black holes are colossal objects, millions to billions of times the mass of the Sun, sitting at the centers of most galaxies. Their immense gravity shapes the dynamics of their surroundings, influencing how stars, gas, and even galaxies themselves behave. These behemoths are among the most enigmatic structures in the universe. In the Milky Way, the supermassive black hole is known as Sagittarius A*. It is about 4 million times the mass of the Sun and lies roughly 26,000 light-years from Earth. Observations of stars orbiting this invisible object have confirmed its existence and provided precise measurements of its mass. Supermassive black holes are thought to grow over time by consuming matter and merging with other black holes. As gas and debris spiral inward, they form an accretion disk around the black hole, heating up and releasing enormous amounts of energy. This process can make the surrounding region one of the brightest in the universe. Some galaxies harbor active supermassive black holes called active galactic nuclei, or AGN. These black holes emit jets of energy and particles, extending thousands of light-years into space. These powerful outflows shape their host galaxies, regulating star formation and altering the distribution of matter. The formation of supermassive black holes remains a mystery. They might have started as smaller black holes, growing by accreting matter over billions of years. Alternatively, they could have formed directly from massive gas clouds in the early universe, collapsing under their own gravity. Their presence at the centers of galaxies suggests a deep connection between black holes and galactic evolution. Observations show a relationship between the mass of a galaxy's central black hole and the properties of its stars, indicating that the two grow together over time. This interplay is known as the black hole galaxy coevolution model. Supermassive black holes are also linked to quasars, some of the most luminous objects in the universe. Quasars are powered by active supermassive black holes consuming matter at incredible rates, creating light that can outshine the entire host galaxy. These objects give us a glimpse into the universe's distant past. Gravitational waves have opened a new way to study these giants. When two supermassive black holes merge, they produce ripples in spacetime that can be detected across vast distances. These signals offer valuable insights into how galaxies and their central black holes evolve through collisions. Even dormant supermassive black holes like Sagittarius A** influence their galaxies. Their gravitational pull stabilizes orbits and affects the distribution of stars and gas. They also act as cosmic anchors, helping to maintain the structure of their host galaxies over time. Some supermassive black holes are thought to form in environments rich with dark matter. The gravitational interactions between ordinary matter and dark matter might have created the ideal conditions for their growth. Understanding this relationship could reveal more about the dark matter's role in cosmic evolution. The study of supermassive black holes has advanced significantly with tools like the Event Horizon Telescope. This global network of observatories produced the first ever image of a black hole's shadow, revealing details of the supermassive black hole at the center of the galaxy M87. These giants are more than cosmic curiosities. They are engines of transformation, driving processes that shape galaxies and influence the universe on vast scales. By studying them, we unlock secrets about how the cosmos operates and evolves, connecting the smallest scales to the largest. Black holes have a profound effect on the fabric of spacetime, warping it in ways predicted by Einstein's theory of general relativity. Their immense gravity creates deep wells in spacetime, bending the paths of light and matter that pass nearby. This warping shapes the behavior of objects in their vicinity and reveals the true nature of gravity. The closer an object gets to a black hole, the more extreme the distortion of spacetime becomes. Light from nearby stars can bend around the black hole, creating visual effects like gravitational lensing. This bending allows us to study the regions near black holes, even though the objects themselves are invisible. Time behaves differently near a black hole due to its intense gravitational field. An observer far from the black hole would see time slow down for anything approaching the event horizon. This effect, called gravitational time dilation, highlights the interplay between time and gravity in extreme environments. The warping of spacetime can also produce unique structures around black holes, such as the photon sphere. This is a region where light is trapped in a circular orbit due to the black hole's gravity. It represents a critical point between escape and capture, illustrating the delicate balance of forces at play. Black holes influence spacetime on a grand scale, creating ripples known as gravitational waves. When massive objects like black holes collide or merge, they generate waves that propagate outward at the speed of light. These waves carry information about the event, allowing us to study cosmic phenomena from vast distances. Rotating black holes, known as Kerr black holes, have an even more dramatic effect on spacetime. Their spin creates a phenomenon called frame dragging, where spacetime itself is twisted and pulled around the black hole. This effect alters the motion of nearby objects and adds complexity to the black hole's surroundings. The event horizon marks a point where spacetime is so warped that escape is impossible. Beyond this boundary, the curvature becomes infinite as it approaches the singularity. This extreme distortion challenges our understanding of physics and raises questions about the nature of space and time. Black holes also provide insights into the relationship between spacetime and quantum mechanics. At the event horizon, quantum effects may play a role in processes like Hawking radiation, where black holes slowly lose mass by emitting particles. This phenomenon bridges two major theories of physics. The study of black holes has revealed that spacetime is not a rigid framework, but a dynamic, flexible entity. Black holes stretch, bend, and reshape spacetime in ways that highlight its interconnectedness with matter and energy. These distortions affect everything from the motion of stars to the expansion of the universe itself. Extreme simulations of black holes help scientists understand how spacetime behaves under the most intense conditions. These models recreate scenarios like the merging of black holes, showing how space-time responds to the colossal release of energy and momentum. Black holes are also thought to play a role in cosmic evolution by affecting the distribution of matter and energy. Their gravitational influence can guide the formation of galaxies, while their interaction with space-time generates patterns that shape the cosmic web. The relationship between black holes and the fabric of space-time is a reminder of the universe's complexity. They stretch our understanding of physics, challenging us to explore deeper into the nature of reality itself. Their existence offers a glimpse into the interplay of forces that define the cosmos. Wormholes are theoretical shortcuts through space-time, connecting distant regions of the universe or even different universes. Predicted by Einstein's equations, they are often visualized as tunnels with two ends, creating a bridge across vast cosmic distances. If they exist, wormholes could revolutionize our understanding of travel and connectivity in the universe. One idea suggests that wormholes might naturally form in extreme environments, such as near black holes. These structures would be incredibly unstable, collapsing almost instantly without some form of stabilization. Exotic matter with negative energy is theorized as a potential stabilizer, but its existence remains unproven. Wormholes are closely tied to the concept of parallel universes. If a wormhole connects two separate universes, it could provide a passage between them. This raises the possibility that our universe is just one of many, linked by hidden pathways through space-time. Some scientists propose that wormholes could exist at quantum scales, fluctuating in and out of existence within the fabric of space-time. These quantum wormholes might not allow for travel, but they could play a role in the underlying structure of the universe. Their existence would have profound implications for physics. Theoretical models also explore the idea of traversable wormholes, which could permit matter or information to pass through safely. While highly speculative, such wormholes might one day enable faster-than-light travel, bypassing the limitations of traditional space exploration. The connection between wormholes and black holes is a subject of intense study. Some theories suggest that certain types of black holes could act as one end of a wormhole. However, the extreme conditions near a black hole would make entering such a structure perilous. Parallel universes, often discussed alongside wormholes, challenge our perception of reality. In some interpretations of quantum mechanics, every decision or event creates a branching universe, leading to an infinite multiverse. Wormholes, if real, could be the bridges connecting these alternate realities. Cosmic inflation theories also hint at the possibility of parallel universes. During the rapid expansion of the early universe, separate regions of space-time might have developed independently, creating disconnected universes. Wormholes could offer a way to explore these isolated realms. Some hypotheses suggest that wormholes might have formed naturally in the early universe. These primordial wormholes could still exist, hidden within the cosmic web, waiting to be discovered. They might even leave subtle imprints on the universe, detectable through gravitational waves or other phenomena. The mathematics of wormholes and parallel universes challenges the limits of our understanding. Both concepts require extending Einstein's general relativity into realms where quantum mechanics also plays a role. This intersection could reveal new principles governing the universe. While no direct evidence for wormholes or parallel universes has been found, their theoretical framework inspires ongoing exploration. Scientists use advanced simulations, astronomical observations, and particle physics experiments to search for clues that might confirm their existence. These ideas stretch the imagination, offering glimpses into possibilities that transcend our everyday experience. Wormholes and parallel universes remind us that the universe is far more complex and mysterious than we can currently comprehend, encouraging us to keep questioning and exploring. The multiverse is a concept suggesting that our universe is just one of many, each existing within a broader reality. These universes may have different physical laws, constants, or even dimensions of space and time. The idea challenges the notion of a singular cosmos, opening up a realm of infinite possibilities. One type of multiverse theory arises from cosmic inflation. During the rapid expansion of the early universe, separate regions of space-time might have expanded independently, creating disconnected universes. Each of these regions could be a self-contained universe with its own properties. Another approach comes from quantum mechanics, specifically the many worlds interpretation. This theory suggests that every decision or quantum event splits reality into multiple branches. Each branch represents a different outcome, creating a constantly growing tree of parallel universes. String theory introduces the idea of a multiverse based on extra dimensions. In this framework, our universe is a three-dimensional membrane, or brane, floating in a higher dimensional space. Other branes could host their own universes, existing alongside ours but invisible to us. The landscape multiverse is another concept from string theory. It proposes that different regions of a vast multiverse have distinct values for physical constants. These variations arise from the way extra dimensions are compactified, leading to universes with unique characteristics. The cyclic multiverse envisions an endless sequence of universes. In this model, each universe begins with a Big Bang and ends with a Big Crunch, followed by a new cycle. This theory suggests that universes are born, evolve, and die in a perpetual loop. The bubble multiverse theory describes a scenario where universes form as bubbles within an inflating sea of space-time. Each bubble represents a distinct universe, and collisions between bubbles could leave observable imprints on the cosmic microwave background. Some multiverse theories arise from mathematics, proposing that all logically possible realities exist. This concept, known as the mathematical multiverse, views universes as structures governed by consistent mathematical rules, regardless of their physical properties. The holographic multiverse suggests that different universes might be projections of the same underlying reality. This idea stems from the holographic principle, which posits that information about a higher dimensional space can be encoded on a lower dimensional surface. Black holes might also play a role in multiverse theories. Some hypotheses propose that new universes could form inside black holes, with the event horizon acting as a bridge between parent and offspring universes. This idea links the death of stars to the birth of new cosmic realms. The simulated multiverse takes a technological approach, suggesting that our universe could be a simulation created by an advanced civilization. If simulations can host conscious beings, then multiple simulated universes could exist within a single overarching reality. These theories challenge us to expand our understanding of existence. Each multiverse concept offers a unique perspective on the nature of reality, highlighting the complexity and vastness of what might lie beyond our observable universe. They remind us that what we know could be just a tiny fraction of the whole. Evidence supporting multiverse possibilities is often indirect, emerging from observations that hint at realities beyond our own. While no direct proof exists, certain phenomena in physics and cosmology align with the predictions of multiverse theories. These clues inspire deeper exploration into what lies beyond the observable universe. One piece of evidence comes from the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Some researchers have identified anomalies, such as cold spots or unusual patterns, which could be the result of collisions between our universe and others. These imprints might provide a glimpse into interactions with parallel realities. The theory of cosmic inflation offers another hint. The rapid expansion of space-time suggests that separate regions could have inflated at different rates, creating isolated universes. This framework naturally leads to the idea of a multiverse as an outcome of the inflationary process. Quantum mechanics adds another layer of support through the many worlds interpretation. In experiments like the double-slit test, particles appear to exist in multiple states simultaneously until observed. This behavior aligns with the idea that every possibility creates a branching universe. The fine-tuning of physical constants in our universe also points toward a multiverse. The values of these constants, such as the strength of gravity or the charge of the electron, seem perfectly calibrated to support life. A multiverse could explain this as a selection effect, with countless universes having different properties. Gravitational waves provide a potential avenue for indirect evidence. If two universes have collided in the past, the resulting shock waves might leave traces detectable by advanced instruments. Observing such patterns would be a groundbreaking step in multiverse research. Black holes offer another intriguing possibility. Some theories suggest that new universes could form within black holes, with their event horizons acting as gateways. If true, studying black holes could reveal connections between our universe and others. Theoretical predictions from string theory also lend support to the multiverse. The vast number of solutions to string theory equations implies a landscape of possible universes, each with unique properties. This mathematical diversity mirrors the concept of a multiverse on a grand scale. Certain patterns in the distribution of galaxies might provide indirect hints of multiverse interactions. Deviations from expected clustering or alignment in the large-scale structure of the universe could point to influences from beyond our cosmic horizon. Simulations of cosmic inflation suggest that multiverses could leave subtle imprints in the form of temperature or density variations. These features might be detectable in future observations, offering a way to test the predictions of multiverse models. Laboratory experiments in particle physics may also hint at multiverse possibilities. Unusual results or deviations from the standard model could indicate interactions with parallel universes or hidden dimensions. Such findings would bridge the gap between theory and observation. While evidence remains speculative, the growing consistency between multiverse theories and certain cosmic observations is compelling. These clues invite us to continue exploring, searching for patterns and phenomena that might reveal the presence of other universes. Each discovery brings us closer to understanding the full scope of reality. Quantum mechanics introduces the possibility of alternate realities through its principles of superposition and wave function collapse. At the quantum level, particles exist in multiple states simultaneously until observed, a phenomenon that suggests the coexistence of multiple outcomes. This strange behavior forms the basis for the idea of alternate realities. The many-worlds interpretation of quantum mechanics expands on this, proposing that every possible outcome of a quantum event actually occurs. Each decision or measurement splits the universe into separate branches, creating an ever-growing multiverse. In this view, all alternate realities exist in parallel, yet are inaccessible to one another. Experiments like the double-slit test demonstrate the peculiar nature of quantum mechanics. When particles like electrons or photons pass through a barrier with two slits, they create an interference pattern, as though they traveled through both slits simultaneously. Observing the particles forces them to choose a path, hinting at the existence of multiple potential realities. Quantum entanglement provides another glimpse into the interconnectedness of alternate realities. When two particles become entangled, the state of one instantly determines the state of the other, no matter the distance between them. This instantaneous connection defies classical explanations and suggests deeper layers of reality. At the heart of quantum mechanics is the wave function, a mathematical description of a particle's probabilities. When measured, the wave function collapses into a single outcome, but the many-worlds interpretation suggests that all other possibilities continue to exist in alternate realities. This challenges traditional notions of causality. Quantum computing offers a potential way to explore alternate realities. By leveraging the principles of superposition and entanglement, quantum computers perform calculations across multiple states simultaneously. Some researchers speculate that these computations may involve interactions with alternate quantum states. The concept of quantum tunneling adds to the mystery. In this phenomenon, particles can pass through barriers they seemingly shouldn't be able to cross. Tunneling could provide a pathway for information or energy to traverse between different quantum realities, though this remains speculative. Alternate realities in quantum mechanics also raise philosophical questions about free will and determinism. If every possible outcome occurs in a branching multiverse, then every choice and action exists in some form. This perspective forces us to rethink the nature of decision-making and reality itself. Theories like quantum decoherence attempt to explain why we don't perceive alternate realities directly. Decoherence occurs when quantum systems interact with their environment, causing them to appear classical and stable. While this hides alternate realities from view, it doesn't rule out their existence. Physicists are exploring ways to test these ideas, such as detecting quantum interference patterns that might hint at interactions between realities. Advanced experiments in particle physics and quantum optics aim to uncover phenomena that align with the predictions of alternate realities. The overlap between quantum mechanics and theories of the multiverse creates a rich field of exploration. If alternate realities exist at the quantum level, they could scale up to influence cosmic phenomena. This connection bridges the smallest scales of nature with the largest, weaving a tapestry of possibilities. Quantum mechanics challenges our understanding of existence, suggesting that reality may be far more layered and complex than it appears. Alternate realities, once the realm of science fiction, are now a legitimate area of scientific inquiry, inviting us to delve deeper into the mysteries of the quantum world. Proving the existence of the multiverse is one of the most challenging tasks in modern science. By its nature, the multiverse suggests realms beyond our observable universe, making direct observation nearly impossible. This inherent separation raises questions about whether evidence can ever be obtained. One major obstacle is the lack of interaction between universes. If other universes exist but do not influence ours, there's no way to detect their presence. Without measurable effects, the multiverse remains a hypothesis rooted in mathematical theory. Even if interactions occur, they might be too subtle to detect with current technology. Collisions between universes, for example, could leave imprints in the cosmic microwave background, but identifying these signatures amidst other cosmic phenomena is extraordinarily difficult. Distinguishing them from noise is an ongoing challenge. Testing the many worlds interpretation of quantum mechanics faces similar issues. Alternate realities in this framework are entirely separate, meaning we have no way to confirm their existence. The theory is elegant but relies on assumptions that cannot be directly tested. Theoretical models like string theory predict a multiverse but also introduce vast complexities. The mathematics allows for countless possible universes, each with different physical laws. While this aligns with the idea of a multiverse, it lacks clear experimental predictions to validate the concept. Cosmic inflation provides a plausible mechanism for creating multiple universes, but proving it requires indirect evidence. Observations of the early universe might support inflation, yet confirming the creation of separate universes during this process remains speculative. Technological limitations further hinder progress. Detecting phenomena such as gravitational waves or cosmic imprints linked to other universes demands instruments far beyond our current capabilities. Advancements in these areas may take decades or longer. Philosophical challenges also arise, as the multiverse raises questions about what constitutes scientific proof. If universes are unobservable by definition, some argue they fall outside the realm of empirical science. This debate blurs the line between physics and metaphysics. Some multiverse models predict observable effects, such as subtle shifts in the values of physical constants. However, these predictions are often indistinguishable from variations within our own universe, making them difficult to verify as evidence for a multiverse. Alternate explanations for certain phenomena complicate the case for the multiverse. For example, the fine-tuning of physical constants could result from natural selection-like processes within a single universe. Competing theories challenge the necessity of invoking multiple realities. Efforts to simulate multiverse scenarios are promising but remain theoretical. Advanced computer models can explore how universes might interact or evolve, yet translating these results into testable predictions is a significant hurdle. Simulations often highlight the complexity of proving such ideas. Proving the multiverse requires both scientific creativity and philosophical flexibility. As technology advances and our understanding deepens, new approaches may emerge. For now, the concept remains a compelling yet elusive frontier in the search for ultimate truth. The concept of the multiverse challenges our understanding of existence and forces us to reconsider our place in reality. If countless universes exist, each with its own unique conditions, the significance of our universe may diminish. This perspective raises profound questions about meaning and individuality. In a multiverse, the idea of uniqueness becomes complex. If every possibility is realized somewhere, then each version of ourselves exists in another universe. This challenges the notion of free will and suggests that every decision we make is just one path among infinite outcomes. The fine-tuning of physical constants takes on new meaning in the context of a multiverse. If countless universes exist, then our universe's suitability for life might simply be a coincidence. This removes the need for a special explanation, yet it raises questions about whether chance alone can account for everything. The multiverse also redefines the idea of reality itself. If alternate universes are disconnected and unobservable, what does it mean for them to exist? This leads to philosophical debates about whether reality is defined by observation or by the possibility of existence. The concept of a multiverse intersects with ancient philosophical ideas. Questions about the infinite, the nature of existence, and the possibility of other worlds have been explored for centuries. Modern science gives these ideas new weight, blending metaphysics with empirical inquiry. The multiverse raises questions about purpose and meaning. If our universe is one among countless others, does it have any inherent significance? Some argue that the multiverse enriches the concept of existence, showing that our reality is part of a much larger tapestry. Religious and spiritual interpretations also come into play. For some, the multiverse aligns with the idea of a greater cosmic design, while others see it as conflicting with traditional beliefs. It invites discussions about the intersection of science, faith, and meaning. The many worlds interpretation of quantum mechanics introduces a fascinating philosophical dilemma. If every choice creates a branching universe, then all outcomes exist simultaneously. This reframes the way we think about decision-making and responsibility, suggesting that every possibility is inevitable. The multiverse challenges the boundaries of human knowledge. If some universes are forever beyond our reach, can we claim to truly understand existence? This limitation forces us to confront the limits of science and the role of speculation in expanding our worldview. The concept of infinite universes also raises ethical questions. If all possibilities exist, does that include worlds with unimaginable suffering or perfect utopias? Exploring the implications of infinite variation leads to profound moral considerations about existence and choice. Philosophically, the multiverse encourages humility. It reminds us that what we know about reality might be only a fraction of a much larger picture. This perspective invites both wonder and introspection, urging us to explore the unknown with an open mind. Ultimately, the multiverse blends the physical and the philosophical, pushing the boundaries of how we define reality, meaning, and existence. It challenges us to think beyond the confines of our universe, exploring what it means to be a part of something infinitely vast. The search for extraterrestrial life is one of humanity's most profound endeavors, driven by the question of whether we are alone in the universe. Scientists explore this mystery through a combination of observation, experimentation, and theoretical models. Each discovery brings us closer to understanding the possibilities for life beyond Earth. One focus of the search is identifying planets within the habitable zone of their stars. This region, often called the Goldilocks zone, is where conditions might allow liquid water to exist, a key ingredient for life as we know it. Advances in telescope technology have revealed thousands of exoplanets, many of which fall into this category. Astrobiology seeks to understand the basic requirements for life by studying extreme environments on Earth. Organisms known as extremophiles thrive in places once thought uninhabitable, such as deep ocean vents or acidic hot springs. These discoveries suggest that life could exist in similarly harsh conditions on other planets or moons. Mars has been a primary target for the search, with numerous missions analyzing its surface and atmosphere. Signs of ancient riverbeds, ice caps, and subsurface water hint at a wetter, more hospitable past. Current exploration focuses on detecting organic molecules and other markers that might indicate past or present life. Beyond Mars, icy moons like Europa and Enceladus are promising candidates. These moons are believed to harbor subsurface oceans beneath their icy crusts, kept liquid by heat from tidal forces. Plumes of water vapor erupting from Enceladus suggest the presence of a dynamic environment that could support microbial life. The study of exoplanets has transformed our approach to finding life. Instruments like the Kepler Space Telescope and the James Webb Space Telescope allow us to analyze the atmospheres of distant planets. Detecting biosignatures such as oxygen, methane, or other compounds associated with life is a key goal. Radio astronomy plays a critical role in the search for intelligent life. Programs like SETI, the search for extraterrestrial intelligence, scan the skies for signals that might indicate communication from advanced civilizations. While no confirmed signals have been detected, the effort continues to expand as technology improves. The discovery of extremophiles has also reshaped our understanding of life's potential. If organisms can survive in the vacuum of space or in toxic environments, the range of possible habitats for life widens significantly. This encourages scientists to look beyond Earth-like conditions in their search. Asteroid and comet exploration adds another layer to the search. Organic molecules, including amino acids, have been detected on these bodies, suggesting that the building blocks of life are common in the universe. This raises the possibility that life could be spread through panspermia, where materials are exchanged between planets. Challenges in the search include distinguishing between biological and non-biological sources of detected signals or molecules. For example, methane on Mars could come from geological processes or microbial activity. Developing methods to differentiate these origins is critical to confirming evidence of life. The search for extraterrestrial life is also deeply philosophical, influencing how we think about our place in the universe. The discovery of even the simplest microbial life elsewhere would redefine our understanding of biology and evolution. Finding intelligent life would have profound cultural and scientific implications. Each mission and observation brings us closer to answering this age-old question. Whether life exists beyond Earth remains unknown, but the pursuit itself drives innovation, exploration, and a deeper connection to the cosmos. It's a journey that continues to inspire and challenge humanity. Exoplanet discoveries have revolutionized our understanding of planetary systems, revealing worlds that range from Earth-like to completely alien. Thousands of exoplanets have been identified in our galaxy, each offering unique insights into the potential for habitability. These discoveries expand the possibilities for finding life beyond our solar system. One of the most significant aspects of exoplanet research is identifying planets within the habitable zone of their stars. This zone, often called the Goldilocks zone, is where temperatures might allow liquid water to exist. Water is considered essential for life, making these planets prime candidates for further study. The variety of exoplanets discovered challenges our expectations of what a planet can be. Hot Jupiters, gas giants orbiting perilously close to their stars, defy traditional planetary models. Meanwhile, super-Earths and mini-Neptunes represent classes of planets not found in our own solar system. The Kepler Space Telescope played a pivotal role in this revolution, discovering thousands of planets by monitoring the brightness of stars. Tiny dips in starlight indicated planets passing in front of their host stars, a technique known as the transit method. This data revealed that planets are far more common than once thought. The James Webb Space Telescope has taken this search even further, enabling detailed analysis of exoplanet atmospheres. By studying the light that filters through a planet's atmosphere during a transit, scientists can identify gases that might indicate habitability, such as oxygen, water vapor, or methane. The discovery of exoplanets in multi-star systems adds another dimension to the search. Planets orbiting binary or even trinary stars must navigate complex gravitational forces, yet some manage to maintain stable orbits. These unique environments raise questions about how life might adapt to such conditions. Red dwarf stars, smaller and cooler than the Sun, have emerged as promising hosts for habitable planets. Their habitable zones are closer to the star, making it easier to detect Earth-sized planets. However, these stars are often highly active, with flares that could challenge the development of life. The TRAPPIST-1 system is a standout example, hosting 7 Earth-sized planets, 3 of which lie in the habitable zone. This compact system provides a unique opportunity to study planets with similar compositions in different environments. Observations of TRAPPIST-1 continue to refine our understanding of habitability. Understanding a planet's atmosphere is key to assessing its potential for life. Thick atmospheres like Venus's can create extreme conditions, while thin or non-existent atmospheres, like on Mars, limit the potential for habitability. Detecting atmospheric signatures helps determine which planets merit further investigation. Planetary size and composition also play crucial roles. Rocky planets with the right mass are more likely to retain atmospheres and support liquid water. Gas giants or icy worlds, while unlikely to host surface life, could harbor subsurface oceans or moons with potential for life. The discovery of planets in the habitable zones of distant stars raises profound questions about the universality of life. If conditions similar to Earth exist elsewhere, it increases the likelihood that life might have emerged multiple times across the cosmos. These planets offer a glimpse into the possibilities of other biospheres. Exoplanet discoveries continue to push the boundaries of what we know about the universe. Each new planet adds a piece to the puzzle, helping us understand the diversity of worlds and the factors that might make a planet hospitable to life. The search is a testament to the ingenuity and curiosity that drive human exploration. The Fermi Paradox questions why, in a universe so vast and old, we haven't yet encountered evidence of extraterrestrial civilizations. While countless stars and potentially habitable planets exist, the apparent silence of the cosmos is puzzling. Scientists and philosophers have proposed a range of solutions to this paradox. One possibility is that intelligent life is extremely rare. The conditions required for the emergence of advanced civilizations may be so specific that even in a galaxy with billions of planets, such life might only appear on a handful of worlds. This rarity would make encounters almost impossible. Another solution is the idea that civilizations are short-lived. Advanced societies may tend to self-destruct through war, environmental collapse, or technological accidents. If civilizations rise and fall quickly, the chances of two existing simultaneously become slim. It's also possible that intelligent civilizations are deliberately avoiding contact. They may follow a policy of non-interference, observing less advanced societies like ours from a distance. This idea is sometimes referred to as the zoo hypothesis, where Earth is akin to an exhibit under quiet surveillance. Distance might be another explanation. The sheer scale of the universe makes communication and travel between civilizations exceedingly difficult. Even if signals were sent, they might take thousands or millions of years to reach us, and we might not recognize them when they arrive. Some suggest that we might be looking in the wrong way or for the wrong signs. Advanced civilizations could use communication methods or technologies beyond our understanding. What we interpret as cosmic noise could be meaningful signals we lack the tools to decode. Another possibility is that intelligent life is confined to digital or artificial forms. Civilizations might transcend biological existence, living in simulated realities that don't require interaction with the physical universe. This would make them virtually undetectable to us. It's also conceivable that intelligent life exists, but doesn't find space exploration or communication worth pursuing. They may focus inward, valuing their own worlds and societies rather than reaching out. Such civilizations could thrive without leaving any trace for us to detect. Some theories propose that intelligent life evolves in environments vastly different from our own. If life is based on non-carbon biochemistry or exists in exotic states, we might not recognize it as life at all. This redefines the parameters of our search and highlights the limits of human perspective. The dark forest hypothesis suggests that civilizations avoid making contact out of fear. In a competitive and dangerous universe, broadcasting one's presence could invite destruction. This scenario paints the cosmos as a place where survival depends on staying hidden. It's also possible that we are the first intelligent civilization to arise. The universe is young compared to its expected lifespan, and life may just be getting started. If this is true, humanity could be a pioneer, laying the groundwork for future interstellar communication. Some propose that evidence of extraterrestrial civilizations may already exist, but has been overlooked or misinterpreted. Ancient artifacts, unrecognized phenomena, or even unexplained aspects of our own biology could hold clues we have yet to understand. Each solution to the Fermi Paradox offers a unique perspective on the nature of the cosmos and our place within it. Whether we are alone or one of many, the paradox continues to inspire questions about the universe, life, and the future of human exploration. Alien intelligence might take forms far different from what we expect, shaped by their unique environments and evolutionary paths. While we often imagine humanoid beings, intelligent life could emerge in ways that challenge our understanding of biology and consciousness. These possibilities expand the scope of what alien life might be. One potential form of intelligence is aquatic. On worlds covered in oceans, life could evolve beneath the waves, developing complex societies without ever venturing to land. Such beings might use sound, bioluminescence, or other mechanisms to communicate and navigate their environments. Silicon-based life is another possibility, arising in conditions unsuitable for carbon-based organisms like us. Silicon's chemical properties allow for complex molecular structures, which could serve as the foundation for alien biochemistry. These forms of life might thrive in extreme heat or on rocky planets. Intelligent life might also be microbial, existing as vast networks of cooperative cells or colonies. These microbial collectives could function as a single consciousness, exchanging information through chemical signals. Such intelligence would challenge our notions of individuality and complexity. Planets with high gravity could give rise to life forms built for strength and resilience. These beings might be dense, low-profile organisms adapted to their environment's intense physical forces. Their evolution would reflect the challenges of surviving under such conditions. On the opposite end, life on low-gravity planets or moons might take on sprawling or delicate forms. Floating, jellyfish-like creatures or vast, thin structures could evolve to take advantage of their unique surroundings. Intelligence here might manifest in ways that are difficult for us to comprehend. Some alien intelligences could be energy-based rather than biological. Entities composed of plasma or electromagnetic fields might inhabit stars, gas giants, or other energetic environments. These beings might communicate through bursts of light or radiation rather than sound or physical movement. Artificial intelligence created by alien civilizations could be the most likely form of intelligence we encounter. Advanced species might transition to digital or machine-based existence, leaving behind their biological origins. These entities could exist indefinitely, exploring the universe in ways organic beings cannot. Intelligence could also take planetary forms, where entire ecosystems or biospheres function as a single conscious entity. On such worlds, intelligence might emerge from the interconnectedness of life, with no individual organisms but a unified planetary mind. Collective intelligences might evolve on worlds where cooperation is critical for survival. Swarm-like beings, communicating through pheromones, signals, or hive minds, could develop advanced societies. These collective entities might think and act as one, blurring the line between individual and community. Alien intelligence might also be non-linear, perceiving time differently from us. Beings that experience the past, present, and future simultaneously could have insights beyond our comprehension. Their communication and thought processes would challenge our ability to understand their perspective. Lastly, alien intelligence might exist in forms we cannot even imagine, shaped by physical laws or dimensions entirely different from those on Earth. These beings might be invisible, intangible, or exist in parallel realities, interacting with our universe in ways that are subtle or undetectable. The potential forms of alien intelligence remind us of the vast possibilities the universe holds. They challenge us to expand our imaginations and refine our search for life beyond Earth, preparing us for the unexpected and the extraordinary. The discovery of extraterrestrial life would be one of the most transformative events in human history, reshaping science, philosophy, and culture. Whether microbial or intelligent, finding life beyond Earth would challenge our understanding of biology and the uniqueness of our planet. It would open a new chapter in humanity's exploration of the universe. Scientific fields like astrobiology and biochemistry would be revolutionized. Analyzing alien life forms could reveal entirely new genetic structures, metabolic processes, or biochemistries. These discoveries might help us better understand the origins of life on Earth and the potential for its existence elsewhere. Philosophically, the discovery would force us to re-evaluate humanity's place in the cosmos. For centuries, we have debated whether we are alone in the universe. Evidence of extraterrestrial life would shift this perspective, showing that life is not unique to Earth. Religious beliefs might also be profoundly impacted. Many faiths address humanity's relationship with creation and the universe. Encountering alien life could lead to reinterpretations of spiritual teachings or even new theological frameworks to incorporate the existence of other beings. The search for intelligent extraterrestrial life raises questions about communication. Establishing contact with another civilization would require understanding entirely unfamiliar languages, symbols, or signals. Successfully decoding their messages could transform our knowledge of technology and culture. The social implications of discovering extraterrestrial life would be immense. It could unite humanity under the shared realization that we are part of a much larger cosmic community. Alternatively, it might provoke fear or uncertainty, highlighting the challenges of navigating the unknown. Technological advancements might accelerate as a result of extraterrestrial discoveries. Studying alien technology, if accessible, could provide insights into energy, propulsion, or materials far beyond our current capabilities. These breakthroughs could redefine human progress. The ethical considerations of encountering alien life are significant. For microbial life, questions about contamination and preservation would arise. For intelligent life, issues of cooperation, respect, and shared resources would take on a global and interstellar importance. The discovery could influence our exploration priorities, shifting focus toward regions most likely to host life. Resources might be redirected toward studying specific planets, moons, or distant systems. This new direction could lead to unprecedented levels of scientific collaboration. Cultural impacts would be felt across art, literature, and media. Stories of alien life have long captured human imagination, and a real discovery would inspire new expressions of creativity. These cultural responses would reflect our hopes, fears, and aspirations for interacting with the unknown. If alien civilizations are found, the knowledge that we are not alone could inspire a deeper sense of responsibility. Recognizing ourselves as one of many intelligent species might encourage humanity to address global challenges with greater urgency and cooperation. Finally, the discovery of extraterrestrial life would redefine how we see ourselves. It would remind us that we are part of a vast, interconnected cosmos, full of possibilities we're only beginning to explore. This realization would drive curiosity, innovation, and a renewed sense of wonder about our place in the universe. Time, according to physics, is a fundamental dimension that allows events to be ordered from past to future. It provides the framework for understanding motion, change, and causality in the universe. Unlike space, which has 3 dimensions, time is considered a single, continuous dimension. Einstein's theory of relativity revolutionized our understanding of time, showing that it is not absolute. Instead, time is relative, varying depending on the speed of an observer and the strength of gravitational fields. This means that time can flow differently for different observers depending on their circumstances. Time is deeply connected to space, forming what physicists call spacetime. Spacetime is a 4-dimensional fabric where the 3 dimensions of space are interwoven with time. This unification helps explain how gravity works, as massive objects curve spacetime, influencing the flow of time itself. In the context of relativity, time dilation occurs when an object moves at high speeds or is in a strong gravitational field. For example, a clock on a spacecraft traveling close to the speed of light will tick slower than a clock on Earth. This effect has been experimentally confirmed and plays a crucial role in technologies like GPS. Quantum mechanics offers a different perspective on time, treating it as a background parameter rather than a dynamic entity. In quantum theory, time is used to describe the evolution of systems, but it remains distinct from the probabilistic behavior of particles. Reconciling this with relativity is one of the great challenges of modern physics. The arrow of time refers to the one-way direction in which time seems to flow, from past to future. This flow is closely linked to entropy, the measure of disorder in a system. As entropy increases, time moves forward, providing a thermodynamic explanation for the asymmetry of time. Time is also a key factor in the expansion of the universe. Cosmological models describe how time began with the Big Bang, marking the start of space-time itself. Before this event, the concept of time as we understand it may not have existed, raising profound questions about the nature of beginnings. In some theories, time could be cyclical, with the universe undergoing endless cycles of expansion and contraction. This challenges the linear perception of time and suggests that events may repeat in some form. Such ideas push the boundaries of how we conceptualize time. Time can be stretched or compressed in extreme conditions, such as near black holes. The intense gravity near a black hole's event horizon slows the passage of time relative to distant observers. This phenomenon highlights the flexibility of time under the influence of gravity. The measurement of time relies on periodic phenomena, such as the oscillation of atoms or the rotation of celestial bodies. Atomic clocks, which measure the vibrations of atoms, provide the most accurate way to track time. These clocks are essential for precision in science, technology, and navigation. The question of whether time is fundamental or emergent remains open. Some theories suggest that time might arise from deeper, more basic principles, such as quantum entanglement or the geometry of space-time. If true, this would redefine time as a derived concept rather than a primary one. Time is not just a scientific concept, but a deeply personal and philosophical one. It governs our lives, shapes our memories, and defines our future. Understanding what time is, according to physics, continues to challenge and inspire us, bridging the physical and the metaphysical realms. Time as a dimension is a cornerstone of modern physics, shaping how we understand the structure of the universe. Like the dimensions of space, time provides a framework for describing the position and behavior of objects. Together, time and space form the 4-dimensional continuum known as space-time. In Einstein's theory of relativity, time is treated as a flexible dimension that interacts with space. The passage of time is not constant, but depends on factors like speed and gravity. This relationship between space and time is what allows the universe to operate as a cohesive whole. While spatial dimensions are easy to visualize, time feels different because we experience it linearly. We move forward in time, unable to revisit the past or skip to the future. This perception creates a distinction between time and space, even though they are interconnected. Mathematically, time is often represented as the fourth dimension in equations describing space-time. Unlike the three spatial dimensions, time has a direction, often referred to as the arrow of time. This directional quality is tied to entropy and the second law of thermodynamics. In space-time diagrams, time is typically depicted as a vertical axis, while space occupies the horizontal axes. Events are represented as points or regions, showing their position in both space and time. These diagrams help visualize how time interacts with space under different conditions. Time as a dimension allows for the concept of world lines, which trace an object's path through space-time. Every particle, person, or planet has a world line that connects its past, present, and future. These world lines demonstrate the continuous nature of time within the space-time framework. The dimensional nature of time also enables phenomena like time dilation. As objects approach the speed of light, their motion through the time dimension slows relative to stationary observers. This effect illustrates how time behaves differently depending on an object's movement through space-time. Gravity's influence on time further supports the idea of time as a dimension. Massive objects like planets and stars curve space-time, creating regions where time flows more slowly. This curvature integrates time into the geometry of the universe, showing its inseparability from space. Considering time as a dimension opens the door to theoretical possibilities like time travel. If time is a dimension, it could in theory be navigated like space. Wormholes, loops, or other space-time structures might allow movement backward or forward through time, though such ideas remain speculative. Time as a dimension also plays a role in the causality of events. The order in which events occur depends on their separation in space and time. Relativity reveals that simultaneity is relative, meaning that two observers may disagree on the timing of events depending on their motion. In quantum mechanics, time as a dimension interacts with the probabilistic nature of particles. The evolution of a quantum system is often described in terms of time-dependent equations. Understanding how time operates at quantum scales is a critical area of ongoing research. Time as a dimension transforms our understanding of reality, merging the concepts of space and time into a unified whole. It reveals the complexity of the universe, challenging us to think beyond our everyday experiences. This dimensional view continues to shape our exploration of the cosmos. Relativity and time dilation reveal that time is not a fixed, universal constant. Instead, time flows differently depending on the relative motion of observers or the strength of gravitational fields. This groundbreaking insight comes from Einstein's theories of special and general relativity. In special relativity, time dilation occurs when an object moves close to the speed of light. As its speed increases, time slows down for that object relative to a stationary observer. This means that someone traveling at near light speed would age more slowly than someone at rest. This effect is not just theoretical, it has been confirmed through experiments. High-speed particles in accelerators decay more slowly than those at rest, demonstrating the effects of time dilation. Similarly, precise atomic clocks flown on fast-moving aircraft show measurable differences in time compared to stationary clocks. General relativity introduces another form of time dilation caused by gravity. In regions of strong gravitational fields, time passes more slowly than in weaker fields. For example, clocks closer to the surface of Earth tick more slowly than those at higher altitudes. This gravitational time dilation is evident in the functioning of GPS satellites. These satellites, farther from Earth's gravity, experience time differently than receivers on the ground. Engineers must account for this difference to ensure the accuracy of navigation systems. Time dilation also has profound implications for space travel. If humans were to journey at relativistic speeds, time for them would pass more slowly than for those remaining on Earth. This concept raises intriguing possibilities for interstellar exploration and the nature of aging during long voyages. The interplay between time dilation and black holes is particularly striking. Near a black hole, the intense gravitational field slows time to a crawl relative to distant observers. An object approaching a black hole's event horizon would appear to freeze in time from an outside perspective. Relativity shows that time is intimately connected to the fabric of space-time. The warping of space-time by motion or gravity directly affects how time flows. This challenges the traditional view of time as absolute, replacing it with a dynamic and relative understanding. Time dilation also alters our perception of causality. Events that seem simultaneous to one observer may occur at different times for another, depending on their relative motion. This relativity of simultaneity reveals how time and space are intertwined in surprising ways. The effects of time dilation are not just limited to extreme conditions. Even the small differences caused by everyday motion and gravity are measurable with modern technology. These subtle variations demonstrate the pervasive influence of relativity in our daily lives. Time dilation introduces a sense of elasticity to time, making it adaptable to the conditions of the universe. This flexibility is essential for understanding phenomena like the expansion of the universe, where time behaves differently on cosmic scales. Relativity and time dilation transform our understanding of time, showing it as a malleable dimension shaped by speed and gravity. These principles continue to challenge our perception of reality, revealing the deep connections between time, space, and the forces that govern the universe. The arrow of time describes the one-way direction in which time flows from past to future. Unlike spatial dimensions, time has an inherent asymmetry, which is deeply tied to the concept of entropy. This relationship defines why certain processes occur in one direction and not the other. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy tends to increase over time in isolated systems. This increase gives time its forward direction, as the universe moves from order to disorder. This connection explains why some processes are irreversible. Ice melting, glass shattering, or heat spreading all result in higher entropy and cannot spontaneously reverse. These everyday examples highlight how entropy governs the arrow of time in familiar contexts. The arrow of time also plays a key role in cosmology. The universe began in a highly ordered state with low entropy, as seen in the uniformity of the cosmic microwave background. Over billions of years, the universe has evolved into a more disordered state, with entropy continuing to rise. Gravitational systems add complexity to the arrow of time. While entropy typically involves spreading and mixing, gravity can create order by clumping matter into stars, planets, and galaxies. This apparent contradiction shows how gravity influences entropy in unique ways. The flow of time appears universal, yet it is not directly dictated by the laws of physics. At a microscopic level, the fundamental equations of physics work equally well in reverse. This raises questions about why we perceive a distinct direction for time on macroscopic scales. One explanation is that the initial conditions of the universe set the stage for the arrow of time. The low entropy beginning of the cosmos creates a gradient that drives the progression toward higher entropy. This initial asymmetry may hold the key to understanding time's direction. The arrow of time is also linked to human experience. Memory, causality, and decision-making all rely on the forward flow of time. We remember the past, act in the present, and anticipate the future, reinforcing our perception of time as linear. In theoretical physics, some models propose that the arrow of time could reverse in certain scenarios. These ideas, while speculative, explore whether time's flow might behave differently in other regions of the universe or under extreme conditions. The increase in entropy also has implications for the ultimate fate of the universe. If entropy continues to rise indefinitely, the cosmos may reach a state of maximum disorder known as heat death. In this scenario, all processes would cease, leaving a lifeless, unchanging universe. The relationship between the arrow of time and entropy challenges our understanding of reality. It raises questions about why the universe began in such a low entropy state, and what that implies about its origins. These mysteries remain at the forefront of modern physics. The arrow of time is more than a scientific concept. It's a framework for understanding change, progression, and the nature of existence. Its connection to entropy reveals the intricate balance between order and disorder, shaping the flow of time that defines our lives and the universe itself. Time raises profound philosophical questions that have captivated thinkers for centuries. What is the nature of time, and does it exist independently of human perception? These questions challenge our understanding of reality and the universe's structure. One question asks whether time is an objective feature of the universe or a subjective experience. Does time exist as a fundamental element of nature, or is it a construct of the human mind? This debate explores the boundaries between physical reality and perception. The concept of the present is another source of philosophical inquiry. Why do we experience a continuous now when the past and future also seem to exist? The nature of the present moment remains a mystery, bridging the physical and psychological aspects of time. Philosophers also question whether time flows or is simply an illusion. Some theories suggest that time is static, with all moments existing simultaneously in a block universe. In this view, the flow of time may be a product of human consciousness, rather than a fundamental property of reality. Causality, the relationship between cause and effect, is deeply tied to our understanding of time. Can events influence the past, or is the flow of time strictly forward? These questions become even more complex in the context of relativity and quantum mechanics. The possibility of time travel introduces ethical and logical paradoxes. If one could change the past, would it create alternate realities or erase the original timeline? These dilemmas challenge our understanding of free will and the fixed nature of history. The beginning of time itself is another philosophical enigma. Did time start with the Big Bang, or does it extend infinitely into the past? If time had a beginning, what does that imply about causation and the nature of the universe? The relationship between time and existence raises questions about permanence and change. Is time necessary for something to exist, or could a timeless reality be possible? These ideas push the boundaries of metaphysics, exploring what it means to be. The finiteness of human life gives time a deeply personal dimension. How does our awareness of mortality shape the way we experience time? This question connects the philosophical nature of time to our emotions, decisions, and values. Some philosophies, like those in Eastern traditions, view time as cyclical rather than linear. In these perspectives, time repeats in endless cycles of creation and destruction. This contrasts with the Western notion of time as a one-way progression, offering a different lens on existence. The intersection of time and memory raises questions about how we construct reality. If the past exists only in our memories and the future in our imagination, is time an illusion created by the mind? This perspective explores the subjective experience of time. Philosophical questions about time remind us of its complexity and elusiveness. Time shapes how we think, live, and interact with the universe, yet its true nature remains one of the greatest mysteries. These inquiries challenge us to deepen our understanding of existence itself. The cosmic web is the large-scale structure of the universe, a vast network of filaments connecting galaxies and galactic clusters. These filaments are made primarily of dark matter, with ordinary matter like gas and stars tracing their paths. This web-like structure defines the architecture of the cosmos on the grandest scales. At the intersections of the filaments lie galactic clusters, dense regions containing hundreds or even thousands of galaxies. These clusters are gravitationally bound, held together by the combined mass of dark matter, galaxies, and hot intracluster gas. They represent some of the most massive structures in the universe. The formation of the cosmic web began shortly after the Big Bang. Tiny fluctuations in the density of matter grew under the influence of gravity, creating the first filaments and clusters. Over billions of years, these structures evolved into the intricate patterns we observe today. Dark matter plays a crucial role in shaping the cosmic web. It provides the gravitational scaffolding that pulls ordinary matter into the web's filaments and nodes. Without dark matter, the large-scale structure of the universe would not exist in its current form. Galactic clusters are often surrounded by smaller groups of galaxies, forming superclusters. These superclusters are connected by filaments, creating the cosmic web's interconnected network. This arrangement shows how matter is distributed unevenly across the universe. The gas in galactic clusters emits X-rays due to its high temperature, reaching millions of degrees. Observing this X-ray radiation helps astronomers map the distribution of matter within clusters. These observations provide key insights into the role of dark matter and the dynamics of the cosmic web. Gravitational lensing offers another way to study the cosmic web and clusters. Massive clusters bend and magnify the light of distant galaxies behind them, creating arcs or multiple images. These distortions reveal the distribution of mass, including the invisible dark matter. Filaments of the cosmic web are not just bridges between clusters. They also contain galaxies and star-forming regions. Observing these filaments helps scientists understand how galaxies form and evolve within the web's framework. The filaments act as cosmic highways, channeling matter into clusters. The voids between filaments are vast, empty regions with few galaxies. These voids highlight the stark contrast between the dense nodes and the sparse expanses of the cosmic web. Studying voids helps astronomers understand the balance between gravitational forces and the universe's expansion. Galactic clusters are dynamic environments, with galaxies interacting and merging over time. These interactions can trigger star formation or disrupt galaxies, altering their structure. The behavior of galaxies within clusters provides clues about the evolution of the universe. Simulations of the cosmic web, based on observations and theoretical models, recreate the formation of filaments and clusters. These simulations match the large-scale patterns observed in the universe, confirming the influence of dark matter and the laws of gravity. The cosmic web and galactic clusters reveal the interconnectedness of the universe, showing how matter organizes itself on the largest scales. By studying this structure, we gain insight into the forces that shape the cosmos and continue to drive its evolution. Gravity is the fundamental force responsible for shaping the structure of the universe. From the smallest particles to the largest galaxy clusters, gravity drives the formation, movement, and evolution of matter. Its influence connects everything in the cosmos, weaving together the fabric of space-time. After the Big Bang, gravity acted on tiny fluctuations in the density of matter, amplifying them over time. These initial differences created regions where matter began to clump together, forming the seeds of stars, galaxies, and clusters. Gravity transformed a nearly uniform universe into the complex structures we see today. As stars formed, gravity pulled them into galaxies, binding them in orbit around a central mass. These galactic systems rely on gravity to maintain their shape and stability, preventing stars from dispersing into space. Without gravity, galaxies could not exist as cohesive structures. On larger scales, gravity draws galaxies toward one another, creating groups and clusters. These massive structures are bound together by the collective pull of their combined mass, including dark matter. Gravity's reach extends far beyond individual galaxies, influencing the distribution of matter across the universe. Dark matter plays a critical role in amplifying gravity's effects. Invisible to light but detectable through its gravitational influence, dark matter forms halos around galaxies and clusters. These halos enhance the gravitational pull, shaping the motion of stars and gas within them. Gravity also governs the formation of stars and planets. As clouds of gas and dust collapse under their own weight, they form dense cores that ignite nuclear fusion, creating stars. This same process gathers debris into planets, moons, and other celestial bodies. In galaxy clusters, gravity holds together not only galaxies but also vast amounts of hot gas. This gas, heated to extreme temperatures, emits X-rays, providing a way to study the cluster's mass and structure. Gravity's role in clustering reveals how matter is distributed on cosmic scales. The filaments of the cosmic web stretching between clusters are also shaped by gravity. These structures channel matter into nodes, feeding the growth of galaxies and clusters. Gravity's pull creates the intricate network that defines the large-scale structure of the universe. Gravitational lensing, where massive objects bend light from distant sources, is another example of gravity shaping our view of the cosmos. This effect not only confirms gravity's strength, but also allows astronomers to map the distribution of both visible and dark matter. Supermassive black holes at the centers of galaxies demonstrate gravity's extremes. Their immense pull affects nearby stars, gas, and even the shape of galaxies. Gravity here operates on scales so intense that it warps space-time itself. Gravity also balances the expansion of the universe. Early on, it slowed the rate of expansion, allowing structures to form. Today, it competes with dark energy, which accelerates the universe's growth. This interplay between gravity and dark energy shapes the cosmos' ongoing evolution. The role of gravity in shaping structure highlights its unifying power. It creates order out of chaos, binding matter into stars, galaxies, and clusters. Gravity's influence connects the smallest particles to the largest cosmic systems, forming the backbone of the universe. Large-scale voids and filaments are the defining features of the cosmic web, showcasing the universe's structure on the grandest scales. Voids are vast, empty regions with few galaxies, while filaments are dense thread-like regions connecting clusters of galaxies. Together they reveal the intricate balance of matter and emptiness in the cosmos. Voids are some of the largest structures in the universe, spanning hundreds of millions of light-years. These regions contain a much lower density of matter compared to their surroundings, with only a few isolated galaxies scattered within them. They highlight the uneven distribution of matter shaped by gravity and expansion. Filaments, by contrast, are where most of the universe's visible matter resides. These elongated structures are composed of galaxies, gas, and dark matter, stretching across millions of light-years. They form the skeleton of the cosmic web, linking nodes of galaxy clusters and superclusters. The formation of voids and filaments began shortly after the Big Bang. Tiny fluctuations in the density of matter grew under gravity, pulling material into filaments and leaving behind vast empty spaces. This process unfolded over billions of years, creating the large-scale patterns we observe today. Voids play a critical role in understanding the expansion of the universe. Because they are dominated by dark energy, they expand faster than denser regions. This behavior provides a natural laboratory for studying the effects of dark energy on cosmic scales. Filaments act as highways for matter, funneling gas and galaxies into dense regions like clusters. These flows drive the growth of large-scale structures, feeding the development of galaxies and the formation of stars. Without filaments, the universe would lack its interconnected framework. The transition from voids to filaments reveals the universe's diversity. At the edges of voids, matter begins to cluster, forming walls and filaments. These boundaries are dynamic regions where gravitational forces shape the movement of galaxies and gas. Observing voids and filaments helps astronomers map the distribution of dark matter. While dark matter is invisible, its gravitational effects influence the formation and alignment of structures. By studying these patterns, scientists gain insights into the unseen components of the universe. The interplay between voids and filaments also affects galaxy evolution. Galaxies in voids tend to be isolated and evolve more slowly, while those in filaments experience more interactions, mergers, and star formation. This contrast highlights the importance of environment in shaping galaxies. Gravitational lensing offers a way to study filaments as their mass bends the light of distant objects. By analyzing these distortions, astronomers can trace the distribution of matter along filaments, revealing their structure in unprecedented detail. The discovery of cosmic supervoids, which are even larger and emptier than typical voids, adds another layer of complexity. These enormous regions challenge our understanding of the universe's uniformity and raise questions about how such vast emptiness can exist. Large-scale voids and filaments illustrate the balance between gravity and expansion, shaping the universe into a web of matter and emptiness. Their study reveals the hidden forces at work, providing a window into the structure and evolution of the cosmos on the largest scales. The cosmic microwave background is the faint glow of radiation left over from the Big Bang, a relic of the universe's earliest moments. It fills the cosmos, providing a snapshot of the universe as it existed about 380,000 years after its birth. Observing this ancient light allows us to peer back in time and understand the origins of the cosmos. First detected in 1964, the cosmic microwave background, or CMB, is considered one of the most important discoveries in cosmology. Its uniform presence across the sky confirmed that the universe began in a hot, dense state. This radiation is a cornerstone of the Big Bang theory, providing evidence for the universe's early conditions. The CMB is not perfectly uniform. It contains tiny fluctuations in temperature and density. These variations represent the seeds of all the structure in the universe today, from galaxies to galaxy clusters. Mapping these fluctuations reveals how matter began to clump together under the influence of gravity. Sensitive instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have provided detailed maps of the CMB. These observations show subtle patterns that reflect the distribution of matter and energy in the early universe. These patterns offer a wealth of information about the cosmos's age, composition, and geometry. The CMB's temperature is remarkably consistent, about 2.7 degrees above absolute zero. but small deviations carry critical clues. Hot and cold spots in the CMB indicate regions of slightly higher or lower density. These regions set the stage for the formation of the cosmic web we see today. Polarization in the CMB provides additional insights. This faint twisting of light reveals how the universe's first structures interacted with radiation. Studying polarization patterns helps cosmologists refine their models of inflation and the distribution of dark matter. Gravitational waves from the early universe could leave imprints on the CMB. Detecting these signals would provide direct evidence of cosmic inflation, the rapid expansion that occurred moments after the Big Bang. This would confirm key predictions about the universe's origins. The CMB also helps determine the universe's age and expansion rate. By analyzing its characteristics, scientists have calculated that the universe is approximately 13.8 billion years old. This data aligns with other observations, strengthening our understanding of cosmic history. Observations of the CMB have revealed the universe's composition, showing that it is made up of about 5% ordinary matter, 27% dark matter, and 68% dark energy. These proportions shape the evolution of the cosmos, influencing everything from galaxy formation to its ultimate fate. The CMB provides a unique opportunity to test theories about the universe's geometry. Its patterns suggest that the universe is flat on large scales, meaning parallel lines would never meet. This finding supports the idea of an infinite or vastly expansive cosmos. While the CMB is a relic of the past, it continues to influence cosmology's future. Advanced observatories are constantly refining our measurements, seeking new details in this ancient light. Each discovery from the CMB brings us closer to understanding the universe's origins and evolution. The cosmic microwave background is more than a glow in the sky. It is a cosmic time capsule. By observing and studying it, we unravel the story of the universe's first moments, providing a foundation for our exploration of the cosmos on every scale. The ultimate shape of the universe is a question deeply tied to its geometry and destiny. On the largest scales, the universe can be open, flat, or closed, depending on the balance between its expansion and the pull of gravity. Observing the universe's structure helps determine which of these shapes it takes. A flat universe is one where parallel lines remain parallel forever, and the geometry follows the familiar rules of Euclidean space. This shape suggests that the universe's expansion is finely balanced, with just enough matter and energy to prevent it from curving. Observations of the cosmic microwave background strongly support this model. In a closed universe, space curves inward like the surface of a sphere. Here, parallel lines would eventually meet, and the universe would have a finite size, though it might not have any boundaries. If the universe is closed, its expansion could one day reverse, leading to a big crunch. An open universe curves outward like the surface of a saddle, with parallel lines diverging over time. In this scenario, the universe would expand forever, growing colder and emptier as galaxies drift apart. This shape suggests a universe with less matter and energy than needed to halt its expansion. The universe's shape is influenced by its density of matter and energy, which determines how space-time is curved. Scientists measure this density using the critical density as a baseline, comparing the actual density to the amount needed for a flat geometry. This comparison reveals whether the universe is open, flat, or closed. Dark energy plays a crucial role in shaping the universe's geometry. Its repulsive force accelerates expansion, counteracting the effects of gravity. A flat universe with dark energy suggests that this mysterious force dominates the cosmos, guiding its ultimate fate. Gravitational lensing provides evidence for the universe's shape by revealing how light bends around massive structures. These observations show that space-time is curved on smaller scales, but appears flat when viewed across vast distances. This consistency strengthens the case for a flat universe. The universe's shape also affects its expansion history. In a closed universe, the expansion slows over time and could eventually reverse. An open or flat universe would continue expanding indefinitely, with the rate of growth depending on the influence of dark energy. While the observable universe appears flat, it is only a portion of the entire cosmos. The ultimate shape could differ beyond our horizon, with regions of space we cannot yet observe. This possibility raises questions about the true size and nature of the universe. Cosmic inflation provides clues about the universe's shape, suggesting that rapid expansion smoothed out any initial curvature. This process would explain why the observable universe appears flat, even if its larger-scale geometry is more complex. Inflation offers a framework for understanding these early conditions. The universe's shape is not just about geometry, it connects directly to its fate. A closed universe might end in a big crunch, while an open or flat universe could lead to a big freeze. Understanding its shape helps us predict the long-term evolution of everything within it. The search for the universe's ultimate shape continues to push the boundaries of observation and theory. Each new measurement refines our understanding, bringing us closer to answering one of the most profound questions about the cosmos and its infinite possibilities. The Big Freeze scenario envisions a universe that continues expanding indefinitely, growing colder and darker over time. As galaxies drift further apart, the density of matter decreases and energy becomes more diffuse. This gradual cooling marks the slow decline of the cosmos. In this future, stars will eventually exhaust their nuclear fuel and cease to shine. The universe will be left with remnants like white dwarfs, neutron stars, and black holes. Without new star formation, the cosmos will lose its sources of light and heat. Over billions of years, even the largest structures will begin to disintegrate. Galaxies will no longer hold together as their stars are scattered across space. Gravity's weakening influence will allow these once dense regions to fade into isolation. Dark energy is the driving force behind the Big Freeze, accelerating the universe's expansion. As space stretches, dark energy prevents gravity from halting or reversing the growth of the cosmos. This acceleration ensures that distant galaxies move beyond our observable reach. As the expansion continues, the cosmic microwave background will cool further, becoming undetectable. The universe will lose the faint glow that currently offers a glimpse of its origins. This decline symbolizes the end of an era in cosmic evolution. Black holes will dominate the universe's later stages, but even these will not last forever. Over unimaginable timescales, black holes will evaporate through Hawking radiation, releasing their energy back into space. Once the last black hole disappears, only subatomic particles will remain. The matter that remains will eventually decay, leaving a universe filled with low-energy photons and neutrinos. With no significant structures or sources of energy, the cosmos will enter a state of maximum entropy. This state, often called heat death, represents the ultimate equilibrium. In the Big Freeze, the temperature of the universe approaches absolute zero. Motion slows to a halt and no meaningful interactions can occur. The cosmos becomes a vast, empty expanse of darkness, devoid of change or activity. This scenario also affects time. Without processes or events to mark its passage, time as we understand it loses meaning. The concept of before and after becomes irrelevant in a universe frozen in stasis. The Big Freeze highlights the inevitability of entropy as systems move toward disorder and equilibrium. It reflects the consequences of a universe governed by dark energy and the relentless expansion of space-time. This fate is dictated by the fundamental laws of physics. While the Big Freeze paints a bleak picture, it also emphasizes the vastness of cosmic timescales. The universe will persist for countless epochs beyond our lifetimes, evolving in ways that stretch the limits of human imagination. This immense timeline offers a sense of both insignificance and wonder. Understanding the Big Freeze helps us grasp the universe's long-term trajectory. It reminds us of the impermanence of all structures, from stars to galaxies, and the inevitability of change. Even in its final frozen state, the universe remains a testament to the forces that shaped it. The Big Crunch presents an alternate scenario for the universe's ultimate fate, where expansion slows, halts, and reverses under the pull of gravity. In this vision, the universe collapses back in on itself, returning to a dense, hot state. This process would mark the end of the cosmos as we know it. If the universe has enough mass, gravity could eventually overcome the force driving its expansion. The reversal would bring galaxies closer together, intensifying their interactions and triggering collisions on an unprecedented scale. The large-scale structure of the universe would begin to disintegrate. As the collapse accelerates, the temperature of the universe would rise dramatically. Gas clouds, stars, and even planets would be compressed into smaller and smaller regions. The energy released from these processes would flood the cosmos, creating an environment of extreme heat and density. Galaxies would merge into massive clusters, which themselves would be pulled into ever-shrinking regions of space. Black holes would consume much of the matter, merging with one another to form larger and larger singularities. These titanic forces would dominate the universe's final stages. The cosmic microwave background would shift from a faint glow to an intense, blinding radiation. The heat from the collapsing universe would undo the cooling processes that have defined its history, reversing the arrow of time in its thermal properties. Eventually, all matter would be crushed into an incredibly small, dense state. At this point, the universe might resemble its conditions at the moment of the Big Bang, with space-time itself collapsing into a singularity. This moment could signify the end of everything. The Big Crunch raises the possibility of a cyclical universe. Some theories suggest that the end of one universe could lead to the birth of another. This cycle of expansion and collapse might repeat indefinitely, giving rise to an eternal sequence of Big Bangs and Big Crunches. Dark energy complicates the likelihood of a Big Crunch. If dark energy continues to dominate, it will prevent gravity from halting the expansion. However, if dark energy weakens or reverses its effects over time, gravity could regain control and trigger a collapse. The concept of a Big Crunch challenges our understanding of time and space. In a collapsing universe, the laws of physics might behave differently, leading to phenomena that are difficult to predict. Time itself could behave in ways that defy human comprehension. Observations of the universe's current expansion rate suggest that a Big Crunch is unlikely. The accelerating expansion driven by dark energy points toward a different fate. However, changes in cosmic conditions could alter this trajectory, making the Big Crunch a theoretical possibility. The idea of the Big Crunch highlights the dynamic nature of the universe. It reminds us that the cosmos is not static, but constantly evolving, shaped by the interplay of gravity, dark energy, and matter. This potential outcome emphasizes the fragility of cosmic balance. Exploring the Big Crunch scenario offers insight into the forces that govern the universe. While it may not be the most probable outcome, it serves as a powerful reminder of gravity's role and the unpredictable future of the cosmos. The collapse of everything into a singular state would be both an ending and a beginning. The Big Rip hypothesis envisions a universe where dark energy grows stronger over time, tearing apart the very fabric of space-time. In this scenario, the expansion of the universe accelerates to the point that all structures, from galaxies to atoms, are ultimately destroyed. It represents one of the most extreme possible fates for the cosmos. As dark energy intensifies, galaxies would be the first to feel its effects. The gravitational bonds holding them together would weaken, causing stars and gas to drift apart. Over billions of years, these once coherent structures would unravel, leaving isolated stars scattered across space. Eventually, even stars would succumb. The forces binding their matter would be overcome by the relentless pull of dark energy. Stars would disintegrate into their constituent atoms, releasing their energy into the void as they are torn apart. The Big Rip would then target planetary systems. The gravitational ties between stars and their planets would fail, sending planets careening into the expanding void. Moons, rings, and even asteroid belts would follow, dismantling the complex systems we see today. As the timeline progresses, even atomic structures would become unstable. The forces that hold protons, neutrons, and electrons together would weaken under the growing influence of dark energy. Eventually, matter itself would disintegrate into elementary particles. In the final moments of the Big Rip, space-time itself would be stretched to its breaking point. The fundamental structure of the universe, the very fabric of existence, would tear apart. This catastrophic ending would leave behind a featureless expanse with no matter, energy, or time. The driving force behind this hypothesis is a type of dark energy called phantom energy. Unlike the constant density of dark energy in other models, phantom energy becomes more intense as the universe expands. This runaway effect pushes the expansion to an unsustainable extreme. The Big Rip is heavily dependent on the properties of dark energy, which remain poorly understood. Observations suggest that dark energy currently drives the universe's acceleration, but whether it will intensify or remain constant is still uncertain. This uncertainty leaves the Big Rip as a speculative, though possible, outcome. Signs of a potential Big Rip would include an increasing rate of expansion over time. Astronomers are closely monitoring the universe's growth to detect any deviations that might indicate an eventual tear. If observed, these changes would profoundly alter our understanding of cosmic evolution. The Big Rip also challenges traditional concepts of time and space. In this scenario, time would cease to have meaning as the universe disintegrates. Without structure or space-time, the very idea of before and after would dissolve. While the Big Rip is one of the more extreme possibilities, it serves as a reminder of the dynamic nature of the cosmos. It highlights how unknown forces, like dark energy, can shape the universe in ways that defy expectation. The delicate balance of forces driving the universe's expansion underscores the fragility of existence. Studying the Big Rip hypothesis pushes the boundaries of cosmology, offering insights into the nature of dark energy and the ultimate fate of the universe. Whether or not it comes to pass, this theory challenges us to consider the profound and unpredictable forces shaping the cosmos. Entropy plays a central role in shaping the universe's ultimate fate, governing the transition from order to disorder over time. According to the second law of thermodynamics, entropy always increases in isolated systems, pushing the cosmos toward a state of maximum uniformity and equilibrium. This principle defines the progression of cosmic events. As stars burn through their nuclear fuel, they convert ordered energy into less useful forms like heat and radiation. This process contributes to the overall rise in entropy, spreading energy more thinly across the universe. Over time, fewer energy sources remain to sustain complex structures. Entropy also governs the breakdown of large-scale structures. Galaxies, stars, and planets are held together by forces that resist entropy, but these forces weaken as energy dissipates. Over billions of years, these systems will disintegrate, leaving behind a universe dominated by simplicity and randomness. The end stages of the universe are characterized by the concept of heat death, a state of maximum entropy. In this scenario, all energy becomes evenly distributed, and temperature differences, necessary for work and change, disappear. The cosmos reaches thermal equilibrium, ceasing all dynamic processes. Even black holes, which seem impervious to entropy, contribute to its rise. As they consume matter and emit Hawking radiation, they gradually lose mass and energy. This radiation represents one of the last sources of entropy production in the universe's final stages. The connection between entropy and time is fundamental. The increase in entropy provides the arrow of time, giving direction to the flow of events. As the universe approaches maximum entropy, the distinction between past and future becomes less meaningful, blurring the concept of time. Entropy not only dictates the physical processes of the universe, but also influences its potential endings. Whether through heat death, a Big Rip, or another scenario, the rise of entropy ensures that complex structures will eventually dissolve. This inevitability underscores the finite nature of the cosmos. Dark energy adds another dimension to entropy's role in the universe's end. By accelerating expansion, dark energy spreads matter and energy more thinly, hastening the approach to equilibrium. The interplay between dark energy and entropy shapes the ultimate trajectory of the universe. While entropy leads to decay, it also allows for the creation of temporary order. Stars, planets, and life itself emerge as localized decreases in entropy, made possible by the universe's energy flows. These moments of order, however fleeting, add complexity to the cosmic narrative. Entropy challenges the idea of permanence. No matter how resilient a structure may seem, it will ultimately succumb to the relentless drive toward disorder. This principle applies to all levels of the universe, from atoms to galaxies. The rise of entropy has profound philosophical implications. It reflects the inevitability of change, the impermanence of complexity, and the limits of energy. These ideas shape how we understand not just the universe, but also the nature of existence itself. The role of entropy in the universe's end is a testament to the unyielding laws of physics. It defines the direction of time, the fate of structures, and the ultimate destiny of the cosmos. As the universe moves toward simplicity, it reveals the profound balance between creation and decay. New discoveries are continuously reshaping our predictions about the universe's fate and its fundamental nature. Advances in observational technology, from space telescopes to particle detectors, are uncovering details that challenge and refine our understanding of cosmic evolution. Each breakthrough adds complexity to the story of the universe. The detection of gravitational waves has opened a new window into cosmic events, revealing collisions between black holes and neutron stars. These observations provide direct evidence of processes that shape the universe's structure, offering insights into how matter and energy behave under extreme conditions. High-resolution maps of the cosmic microwave background have refined our understanding of the universe's early moments. These observations reveal subtle patterns that inform models of dark matter, dark energy, and the overall geometry of the cosmos. They help predict the universe's long-term behavior. The discovery of thousands of exoplanets has broadened our perspective on the conditions for life and the potential uniqueness of Earth. By studying planetary systems across the galaxy, scientists are building models that explore how life might emerge and survive in different cosmic scenarios. Observations of distant supernovae have confirmed the accelerating expansion of the universe, driven by dark energy. This acceleration has profound implications for the cosmos's future, suggesting outcomes like the Big Freeze or even the Big Rip. Dark energy remains one of the most enigmatic forces shaping predictions. Simulations of the cosmic web, powered by advanced computing, have recreated the universe's evolution with remarkable accuracy. These models test hypotheses about the role of dark matter and the formation of large-scale structures, providing clues about how the cosmos might continue to evolve. Research into black holes has revealed unexpected phenomena, such as the possibility of Hawking radiation and the intricate structure of event horizons. These findings challenge assumptions about entropy and energy, influencing predictions about the universe's end stages. Studies of the universe's expansion rate have exposed discrepancies between local and cosmic measurements of the Hubble constant. Resolving this tension could lead to new physics, shedding light on the behavior of dark energy or the properties of space-time itself. Breakthroughs in particle physics are probing the nature of fundamental forces and particles, seeking connections to dark matter and dark energy. Discoveries at colliders and detectors may reveal interactions that were previously hidden, shaping our understanding of the universe's unseen components. The observation of primordial gravitational waves, if achieved, could confirm theories about cosmic inflation. This would solidify our understanding of the universe's origins and provide a clearer picture of its large-scale geometry and destiny. Advances in quantum mechanics and the search for a theory of quantum gravity are bridging gaps between relativity and the quantum world. These efforts could reveal how space-time behaves under extreme conditions, altering predictions about black holes, singularities, and the universe's final moments. New discoveries remind us that the universe is far more dynamic and complex than we once imagined. As our tools and theories evolve, so too do our predictions about its fate. Each step forward reveals deeper mysteries, driving humanity's quest to understand the cosmos and its ultimate destiny. The dual nature of particles and waves is one of the most intriguing principles of quantum mechanics, revealing that particles like electrons and photons can behave as both particles and waves. This duality challenges classical ideas of matter and energy, showing that reality operates in ways that defy intuition. The wave-like behavior of particles was first demonstrated in experiments like the double-slit test. When electrons or photons pass through two slits, they create an interference pattern characteristic of waves. Yet when observed directly, these same particles behave like discrete points, suggesting particle-like properties. This duality is not limited to light, but applies to all matter. Even large molecules, under the right conditions, exhibit wave-like interference patterns. This universality highlights the quantum nature of all particles, regardless of size or composition. The concept of wave-particle duality is formalized in the mathematical framework of quantum mechanics. Particles are described by wave functions, which represent probabilities rather than definite positions or paths. The wave function captures the essence of a particle's dual nature. When a measurement is made, the wave function collapses, and the particle appears in a specific location. This collapse illustrates the transition from wave-like probabilities to particle-like certainty, a process that remains one of the greatest mysteries in physics. The wavelength of a particle is inversely proportional to its momentum, as described by the de Broglie equation. For everyday objects with large momentum, the wavelength is so small that wave-like behavior is imperceptible. However, at the quantum scale, these effects become significant. Wave-particle duality also underpins technologies like electron microscopy. By treating electrons as waves, these devices achieve resolutions far beyond conventional light microscopes. This practical application shows how quantum principles can be harnessed to explore the microscopic world. Photons, the particles of light, provide one of the clearest examples of duality. In some experiments, they act as waves, interfering and diffracting, while in others, they appear as particles, transferring energy in discrete packets called quanta. Their behavior depends on how they are observed. The dual nature of particles and waves extends to energy transfer. Light waves can carry energy across vast distances, while their particle-like nature allows them to interact with matter in precise, quantized amounts. This interplay is the foundation of processes like photosynthesis and solar power. Wave-particle duality also raises philosophical questions about the nature of reality. If particles exist as probabilities until observed, what determines their behavior? This ambiguity challenges the classical view of a deterministic universe, introducing the role of the observer in shaping outcomes. Experiments continue to push the boundaries of wave-particle duality, exploring how quantum systems transition to classical behavior. Understanding this shift may unlock new insights into the connections between the quantum and macroscopic worlds. Wave-particle duality is more than a curiosity. It is a fundamental aspect of nature. It reveals the complexity and interconnectedness of matter and energy, challenging us to think beyond traditional boundaries and embrace the strange beauty of the quantum realm. Quantum entanglement is a phenomenon where two or more particles become interconnected, such that the state of one instantly determines the state of the other, no matter the distance between them. This connection defies classical notions of locality, suggesting that information can be shared across vast distances without any apparent medium. When particles are entangled, their properties such as spin or polarization are correlated. Measuring one particle's state immediately reveals the corresponding state of its partner, even if they are light years apart. This instantaneous effect has been confirmed through numerous experiments, challenging our understanding of causality. Einstein famously referred to entanglement as spooky action at a distance, doubting its implications for physics. He believed it violated the principle that no information can travel faster than light. However, experimental evidence consistently supports entanglement as a real and fundamental aspect of nature. Non-locality, the principle underlying entanglement, suggests that the universe operates on levels beyond traditional space and time. While the particles remain separate in space, their states are connected through the quantum wave function. This connection transcends physical distance, uniting the particles in a shared quantum state. Entanglement plays a key role in quantum mechanics, demonstrating that particles do not have definite properties until measured. Instead, they exist in superpositions of states, with entanglement linking these probabilities across multiple particles. Measurement of one particle collapses the wave function for both, resolving their shared uncertainty. Experiments testing Bell's inequalities have provided strong evidence for the non-local nature of entanglement. These experiments rule out classical explanations, confirming that entangled particles cannot be described by hidden variables within a local framework. The results solidify entanglement as a uniquely quantum phenomenon. Quantum entanglement is not just a theoretical curiosity. It has practical applications in emerging technologies. Quantum cryptography uses entanglement to create secure communication channels, as any attempt to intercept the information disrupts the entangled state. This ensures unparalleled levels of security. Entanglement is also essential for quantum computing, enabling the creation of qubits that can store and process vast amounts of information simultaneously. By leveraging the correlations between entangled particles, quantum computers can solve problems that are impossible for classical systems. The implications of entanglement extend to questions about the nature of reality itself. If particles are connected instantaneously, what does this say about the fabric of the universe? Some interpretations of quantum mechanics suggest that entanglement hints at a deeper hidden layer of interconnectedness. Non-locality challenges the limits of relativity, which posits that no influence can travel faster than light. While entanglement does not transmit information in a conventional sense, its instantaneous correlations suggest that our understanding of space-time may be incomplete. Reconciling these theories remains an open question in physics. Efforts to explore entanglement at larger scales are ongoing, with experiments entangling macroscopic systems and even photons sent to orbiting satellites. These studies aim to push the boundaries of quantum mechanics, testing its validity in new and extreme conditions. Quantum entanglement and non-locality reveal a universe that is more interconnected and mysterious than we might have imagined. They challenge classical assumptions about separateness and causality, offering a glimpse into the profound and hidden relationships that govern the quantum world. The observer effect in quantum mechanics reveals that the act of measurement influences the outcome of a quantum system. Before being observed, particles exist in a state of superposition, where they hold multiple probabilities simultaneously. The moment an observation occurs, the wave function collapses, and the particle adopts a definite state. This phenomenon is most famously illustrated by the double-slit experiment. When particles pass through two slits unobserved, they create an interference pattern, behaving as waves. However, if their path is measured, the interference pattern disappears, and the particles behave like discrete particles. The observer effect raises profound questions about the role of measurement in shaping reality. Does the act of observation create the outcome, or does it simply reveal a pre-existing state? Quantum mechanics suggests that particles do not have definite properties until they are observed. This challenges the classical view of an objective reality that exists independently of observation. In the quantum world, the observer and the observed are intrinsically linked. This interdependence forces us to reconsider the nature of reality itself. The observer effect is not limited to human observation. Any interaction that extracts information from a system constitutes a measurement. This means that even inanimate objects or devices can trigger the collapse of a wave function, demonstrating that observation is a physical process. Theories like the Copenhagen interpretation embrace the observer effect, arguing that the collapse of the wave function is a fundamental aspect of quantum mechanics. Other interpretations, such as the many worlds theory, suggest that all possible outcomes occur, but only one is experienced by the observer. The observer effect also extends to Heisenberg's uncertainty principle, which states that certain properties, like position and momentum, cannot be measured simultaneously with absolute precision. The very act of measuring one property disturbs the system, affecting the other. This highlights the limitations of knowledge in the quantum realm. In quantum cryptography, the observer effect ensures secure communication. Any attempt to intercept a quantum signal alters its state, making tampering immediately detectable. This practical application turns the observer effect into a powerful tool for security. Philosophically, the observer effect raises questions about the role of consciousness. Some interpretations suggest that the presence of a conscious observer influences the outcome of quantum systems, while others argue that observation is purely a physical interaction with no need for awareness. Experiments continue to test the boundaries of the observer effect, exploring whether it operates at macroscopic scales. If quantum behavior can be extended to larger systems, it might reshape our understanding of the transition between the quantum and classical worlds. The observer effect also influences the development of quantum technologies. Understanding how measurement impacts systems allows scientists to design experiments and devices that maximize control over quantum states, enabling advancements in computing, sensing, and communication. The observer effect underscores the profound connection between measurement and reality. It challenges the idea of a detached universe, showing that the act of observation is an integral part of the quantum world. This principle remains at the heart of debates about the nature of existence and the limits of human knowledge. The implications of quantum mechanics for understanding reality challenge the very foundation of how we perceive the universe. At the quantum level, particles exist as probabilities, not certainties, until measured. This idea reshapes our understanding of what is real and how reality is defined. Superposition suggests that multiple possibilities can exist simultaneously, blurring the line between what is potential and what is actual. Reality, in this framework, is not fixed, but emerges through observation and interaction. This concept forces us to rethink the nature of existence. The interconnectedness revealed by quantum entanglement suggests that reality may not be entirely local. The state of one particle can influence another instantly, regardless of distance, hinting at hidden layers of connection underlying the visible universe. This non-locality challenges classical ideas of space and separation. Wave-particle duality introduces a dual framework for describing matter and energy, with particles acting as both waves and discrete units depending on the context. This duality suggests that reality is more fluid and adaptable than traditional physics allows. The observer effect highlights the active role of measurement in shaping reality. Rather than being passive spectators, observers participate in determining outcomes at the quantum level. This interaction raises profound questions about the relationship between consciousness and the physical world. Quantum mechanics suggests that the universe is inherently probabilistic, not deterministic. Events at the quantum level cannot be predicted with certainty, only with probabilities. This indeterminacy challenges the classical idea of a clockwork universe governed by fixed laws. Some interpretations of quantum mechanics, like the many worlds theory, propose that all possible outcomes of a quantum event exist in parallel universes. If true, this means reality is not singular, but part of a vast multiverse where every possibility is realized. The nature of time is also questioned by quantum mechanics. The linear progression of time, as experienced in everyday life, contrasts with the timelessness of quantum equations. This disconnect raises questions about whether time is an emergent property rather than a fundamental aspect of reality. Quantum mechanics has implications for the boundary between the quantum and classical worlds. How and why quantum behaviors transition to classical realities remain open questions. This boundary may hold the key to understanding how the macroscopic world emerges from the microscopic. The role of consciousness in shaping reality is a deeply debated implication of quantum mechanics. Some interpretations suggest that awareness itself may influence quantum states, while others argue that consciousness is not necessary for wave function collapse. This debate bridges physics and philosophy. Advancements in quantum technology, inspired by these principles, continue to blur the line between theoretical and applied physics. Innovations in quantum computing and communication not only exploit quantum principles, but also deepen our understanding of reality's underlying mechanisms. The implications of quantum mechanics remind us that reality is far more complex, interconnected, and mysterious than it appears. It challenges us to embrace uncertainty and redefine our place in a universe governed by probabilities and possibilities. These ideas continue to push the boundaries of science and philosophy. Bridging quantum physics with cosmology seeks to unite the smallest scales of existence with the largest structures in the universe. Quantum physics governs the behavior of particles and forces at the microscopic level, while cosmology explores the vastness of space-time and the evolution of the cosmos. Connecting these realms could unlock profound insights about the universe. The early universe provides a natural link between these two fields. During the first fractions of a second after the Big Bang, quantum effects dominated, shaping the distribution of matter and energy. These quantum fluctuations were stretched by cosmic inflation, seeding the structures we observe today. Cosmic inflation itself is deeply tied to quantum theory. The rapid expansion of space-time is thought to be driven by quantum fields, which generate the energy necessary for inflation. Understanding these fields could reveal the mechanisms behind the universe's initial growth. Black holes are another point of connection between quantum physics and cosmology. They bring together the intense gravity of general relativity with quantum effects at their event horizons. Phenomena like Hawking radiation suggest that black holes can emit particles, merging concepts from both domains. The search for a theory of quantum gravity aims to unify these perspectives. General relativity describes gravity as the curvature of space-time, while quantum mechanics treats forces as interactions mediated by particles. A unified theory would reconcile these approaches, offering a complete picture of the universe. String theory is one candidate for bridging quantum physics with cosmology. It proposes that particles are not points but vibrating strings, with different vibrations representing different particles. String theory naturally incorporates gravity and may explain the fabric of space-time on the smallest scales. The quantum nature of space-time itself is a subject of exploration. Some theories suggest that space-time is not continuous, but made up of discrete units at the Planck scale. This granularity could reveal new insights into the behavior of the universe under extreme conditions. Quantum entanglement may also play a role in the structure of space-time. Some researchers propose that the fabric of space-time emerges from the entanglement of quantum particles. This idea hints at a deeper connection between the geometry of the universe and quantum interactions. Dark energy and dark matter, which dominate the universe, remain mysteries that straddle both quantum physics and cosmology. Quantum field theory could explain dark energy as the vacuum energy of space, while dark matter might consist of undiscovered quantum particles. These connections are key to understanding the cosmos. The study of the multiverse bridges these fields as well. If quantum fluctuations can give rise to multiple regions of space-time, each with different properties, the multiverse might emerge as a natural consequence of quantum mechanics. This idea links the microscopic processes to the larger-scale phenomena. Advancements in observational technology are helping to test these theories. Instruments capable of detecting primordial gravitational waves or mapping the cosmic microwave background in greater detail provide data that informs both quantum and cosmological models. Each discovery tightens the bridge between these disciplines. Bridging quantum physics with cosmology is not just about solving technical puzzles. It's about uncovering the underlying principles of reality. By linking the smallest particles to the vastness of the cosmos, we gain a deeper understanding of the universe's origins, structure, and ultimate fate. These efforts continue to push the boundaries of human knowledge. Throughout this journey, we've explored some of the most profound and fascinating aspects of the universe, unraveling mysteries that stretch from the quantum realm to the vast expanse of the cosmos. We began by examining the Big Bang, the moment that set everything in motion, and considered the revolutionary ideas of cosmic inflation and alternative theories about the universe's origins. We delved into the enigmatic forces of dark matter and dark energy, uncovering their roles in shaping the universe's structure and driving its accelerating expansion. Through observations of galactic rotation curves, gravitational lensing, and the large-scale distribution of matter, we pieced together evidence of these invisible components that dominate the cosmos. The concept of the multiverse expanded our perspective, introducing the possibility that our universe is just one of many. We discussed the implications of these ideas, from bubble universes to parallel realities, and explored how quantum mechanics might offer a bridge to understanding these alternate worlds. Time emerged as another central theme, with its definition, nature, and role in the universe's evolution challenging our perceptions of reality. From relativity's insights into time dilation to the philosophical implications of the arrow of time and entropy, we explored how time connects to the fabric of existence. We ventured into the depths of black holes, examining their formation, event horizons, and singularities, and considered how they shape space-time and influence the galaxies around them. Their connection to cosmic phenomena and their potential role in linking different universes pushed the boundaries of our imagination. Quantum mechanics offered another dimension to our exploration, with its principles of wave-particle duality, entanglement, and the observer effect reshaping our understanding of reality. These concepts challenge the very fabric of how we perceive and interact with the universe. We considered the universe's ultimate fate, from the chilling stillness of the Big Freeze to the dramatic collapse of the Big Crunch, and even the catastrophic unraveling of the Big Rip. Each scenario painted a vivid picture of the forces shaping the cosmos and the potential endings it might face. Observational advancements from mapping the cosmic microwave background to detecting gravitational waves have continually refined our predictions and expanded our knowledge. These tools not only reveal the universe's past, but also guide us toward understanding its future. Finally, the connection between quantum physics and cosmology highlighted the unity of all scales of existence. Whether through black holes, the multiverse, or the fabric of space-time itself, bridging these fields illuminates the intricate links between the smallest particles and the largest cosmic structures. If you've enjoyed this deep dive into the universe's secrets, don't forget to like the video and subscribe to the channel. There's so much more to discover, and our other videos cover topics that continue this exploration of science, philosophy, and the wonders of the cosmos. Thank you for watching, and we'll see you in the next adventure.